There is a world hiding in the space between Mars and Jupiter that almost no one has ever heard of. It is larger than most countries on Earth. It is darker than coal, and it is perfectly, impossibly round. For more than 170 years, astronomers called it an asteroid, a lump of rock, a piece of debris, a leftover from the formation of the solar system that did not deserve a second thought. It sat in catalogues, buried under thousands of other minor bodies, dismissed as ordinary. No mission was ever sent to visit it. No faint photograph was ever taken of it. No child ever built a model of it for a school project. It was, in every sense of the word, ignored. But in 2019, a team of scientists pointed one of the most powerful telescopes on Earth directly at it. They used an instrument so advanced that it was originally designed to photograph planets orbiting distant stars, worlds trillions of kilometers away, lost in the glare of their own suns. This instrument could resolve details that no other ground-based observatory on the planet could match, and when they aimed it at this forgotten asteroid and processed the data, the image that appeared on their screens was something no one had predicted. They saw a sphere, not a jagged boulder, not an irregular chunk of ice and stone, not the potato-shaped lump that nearly every asteroid of comparable size turns out to be when you look closely enough. A sphere, smooth, symmetrical, hauntingly featureless. Almost perfectly round, in the way that planets are round, in the way that worlds are round. And that single observation, captured in a handful of pixels on a monitor inside a mountaintop observatory in Chile's Atacama Desert, threatened to reclassify everything we thought we knew about what counts as a world, what counts as a planet, and where the line between a living body and a dead rock truly falls. Its name is Hygiea. Named after the ancient Greek goddess of health and cleanliness, it orbits the Sun in the asteroid belt, that vast, cold, silent ring of rubble that separates the rocky inner planets from the enormous gas giants beyond. Most people, if they think about the asteroid belt at all, think of it as a wall of tumbling rocks, a hazard course for spacecraft, a chaotic junkyard of solar system leftovers. The reality is both simpler and stranger. The belt is almost entirely empty. The objects within it are separated by distances greater than the gap between the Earth and the Moon. You could fly through it 1,000 times and never come close to hitting anything. But scattered across that emptiness are objects of extraordinary size and complexity, and Hygiea is one of them. Hygiea is the fourth largest object in the entire asteroid belt. Its diameter stretches to roughly 430 kilometers. That is wider than the entire length of England from London to the Scottish border. If you placed Hygiea on a map of Europe, it would cover Austria. If you dropped it into the Pacific Ocean, it would create an island larger than Japan's main island of Honshu. This is not a pebble drifting through space. This is not a chip of rock. This is a body massive enough to have a measurable gravitational field, dense enough to have a meaningful interior structure, and, as of 2019, round enough to challenge the definition of a planet. And here is where the mystery begins to deepen. The roundness of Hygiea is not just unexpected. By every model of planetary physics that existed before 2019, it is supposed to be impossible. Objects at this size, 430 kilometers, are not supposed to be spherical. The gravitational pull of a body this small should not be strong enough to overcome the structural rigidity of rock and pull it into a sphere. That process, called hydrostatic equilibrium, was thought to require a body at least 600 kilometers across and possibly larger. Below that threshold, gravity loses the battle against the strength of stone, and the object keeps whatever irregular shape it was born with. Every textbook, every model, every simulation agreed on this point. And yet Hygiea is round, not approximately round, not sort of round. Round in the way that only a body in hydrostatic equilibrium, a body whose own gravity has overcome every internal resistance and crushed it into the most efficient geometric shape in nature, is supposed to be. The measurements are unambiguous. The images are clear. Hygiea is a sphere, and it gets stranger. When astronomers finally mapped Hygiea's surface in high enough resolution to see real features, they expected to find something dramatic and unmistakable. A single, colossal impact crater dominating the landscape, like a wound carved into the face of the world. This was not a guess. It was a firm prediction, grounded in decades of evidence. Hygeia is the parent body of one of the largest asteroid families in the belt, a swarm of more than 6,000 smaller asteroids that share its orbit and its dark, carbonaceous composition. Those family members are the debris of an ancient catastrophe, fragments blasted off the original body by a collision so violent it launched enough material to fill a region of space millions of kilometers across. The crater left behind by that collision should be enormous, 200 kilometers wide or more. On a body only 430 kilometers in diameter, it would be impossible to miss. But the crater is not there. The surface of Hygeia is eerily, unnervingly smooth. No massive basin, no towering rim, no rubble field. No sign, anywhere on the surface, of the wound that every model says should be the defining feature of this world. The scar has been erased, and the only explanation that fits the data is one that rewrites Hygeia's entire history. An explanation more violent, more radical, and more unsettling than anyone expected. The impact did not merely scar the surface, it shattered the original body completely. It blew Hygeia apart. Every mountain, every crater, every layer of geological history accumulated over billions of years, destroyed in an instant, reduced to a cloud of rubble and dust expanding into the vacuum of space. Hygeia died. It was annihilated. And then, slowly, over thousands of years, gravity pulled the fragments back together, piece by piece, fragment by fragment. The debris collapsed back inward, settling under its own weight, arranging itself into the most gravitationally stable shape available, a sphere. The body that exists today is not the original Hygeia. It is a reconstruction, a second draft, a world that was destroyed, and then, through nothing more than the patient, relentless pull of gravity, was reborn. This is the story of a world that exists at the edge of a definition, too large to ignore, too round to be a simple asteroid, too small for anyone to care about until now. It is the story of how a handful of images from a telescope in the Chilean desert forced the International Astronomical Union to confront a question it thought it had already settled in 2006. What is a planet? What is a world? And who gets to decide? It is the story of destruction and resurrection on a scale that dwarfs anything in human experience. And it is the story of what happens when the universe builds something that our categories cannot contain. By the end of tonight, you are going to understand why Hygeia might be the most important object in the solar system that no one is paying attention to, why its impossible roundness, its missing crater, and its violent rebirth force us to rethink the line between rock and world, between asteroid and planet, between debris and something that deserves a name. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now let us begin. To understand why Hygeia matters, why a dark, distant, overlooked body in the asteroid belt has become the center of one of the most important debates in modern planetary science. You first need to understand the place where it lives, and the asteroid belt is almost nothing like what most people imagine. In the popular imagination, shaped by decades of science fiction movies and television shows, the asteroid belt is a dense field of tumbling boulders, rocks so tightly packed that a spaceship must weave and dodge at breakneck speed to survive the crossing. Picture the iconic scene from any space adventure, a pilot sweating at the controls, lurching left and right as massive chunks of stone flash past the windshield, scraping the hull, smashing into each other in a constant barrage of destruction. That image is burned into our cultural consciousness. It has shaped the way generations of people think about this part of the solar system. And it is completely, spectacularly wrong. The real asteroid belt is overwhelmingly empty, staggeringly, incomprehensibly empty. If you could teleport yourself to a random point in the belt, you would see nothing. Absolutely nothing. The sun would be a bright but noticeably smaller dot in the sky, and beyond it, only stars. The nearest asteroid to you would be, on average, roughly 1 million kilometers away. More than 2.5 times the distance from the Earth to the Moon. If you had the sharpest eyes in the world, you still would not see it. It would be too far away and too small. You would float in perfect silence, surrounded by a void so vast and so empty that the word loneliness does not begin to capture it. The numbers bear this out. The asteroid belt spans a region from roughly 2.2 to 3.3 astronomical units from the Sun, a ring about 150 million kilometers wide. The total number of known asteroids is now well over 1 million, but even 1 million objects scattered across that volume is less than a whisper. NASA has sent 9 spacecraft through the asteroid belt: Pioneer 10 and 11, Voyager 1 and 2, Galileo, Cassini, New Horizons, Juno, and Lucy, and not a single one has ever come close to hitting anything. The probability of a random collision has been calculated at roughly 1 in 1 billion per crossing. The belt is not a hazard. It is a near-perfect vacuum with a few grains of sand sprinkled across it. And yet, within that vast emptiness, there are objects of extraordinary size. Not millions of them, just a handful, a small population of bodies large enough to have complex geology, layered interiors, and histories as rich and dramatic as any planet. These are the giants of the belt, and understanding them is essential to understanding Hygeia. The largest is Ceres. At roughly 946 in diameter, Ceres is the undisputed ruler of the asteroid belt. It accounts for approximately 1/3 of the belt's total mass, all by itself. If you added up every other object in the belt, Ceres would still outweigh most of them combined. But Ceres is more than just big, it is geologically complex. NASA's Dawn spacecraft, which orbited Ceres from 2015 to 2018, revealed a world far more active and interesting than anyone expected. Beneath Ceres's dark, cratered surface lies a mantle rich in water ice. So much ice that Ceres may contain more fresh water than all the rivers and lakes on Earth combined. Bright deposits of sodium carbonate, a type of salt, dot the surface, carried upward from a briny, subsurface ocean that may still be liquid today. Ceres is not just a rock, it is a world with a hidden ocean, and since 2006 it has been classified as a dwarf planet, the only one in the inner solar system. After Ceres comes Vesta. At roughly 525 kilometers in diameter, Vesta is the second largest body in the belt, and one of the most geologically fascinating small worlds in the solar system. Unlike Ceres, Vesta is dry, dense, and fully differentiated. It has a metallic iron-nickel core, a rocky mantle, and a basaltic crust. In structure, it is a miniature version of Earth. Its surface is scarred by 2 enormous impact basins: Rhea Silvia, near the South Pole, which is 505 kilometers wide and 19 kilometers deep, and the older Venenia Basin beneath it. The Rhea Silvia impact was so violent that it excavated roughly 1% of Vesta's total volume and launched fragments across the solar system. Some of those fragments eventually fell to Earth as meteorites, a type called head meteorites, which account for roughly 5% of all meteorites found on our planet. When you hold an head meteorite, you are holding a piece of Vesta's crust, a fragment that travelled hundreds of millions of kilometers across space before landing in a field or a desert on Earth. Third is Pallas, at approximately 512 kilometers in diameter. Pallas is the oddball of the group. Its orbit is tilted by more than 34 degrees relative to the plane of the ecliptic, by far the most inclined orbit of any large asteroid. This extreme tilt takes Pallas high above and below the plane in which most solar system objects orbit, making it extraordinarily difficult to reach with a spacecraft. As a result, Pallas is one of the least studied large bodies in the inner solar system. We know it exists. We know it is roughly the same size as Vesta. We know it is darker and more carbon-rich. But beyond that, Pallas remains largely a mystery, a world hiding in plain sight, its secrets locked away behind the practical difficulty of getting there. And then there is Hygeia, fourth in line, the smallest of the big four, and, until 2019, by far the most ignored. No spacecraft has visited it, no detailed map exists of its surface, no popular science book devotes more than a footnote to it. In the hierarchy of the asteroid belt, Hygeia has always been the forgotten sibling, present, counted, catalogued, and then overlooked in favour of its larger and more photogenic neighbours. The story of how humanity found these bodies, and how Hygeia quietly entered the historical record, begins at the turn of the 19th century, in an era when the very concept of an asteroid did not yet exist. For centuries, astronomers had known the distances to the 6 visible planets: Mercury, Venus, Earth, Mars, Jupiter, and Saturn. They had measured their orbits with increasing precision. and some had noticed something curious about the spacing. In 1766, a German astronomer named Johann Daniel Titius observed that if you took the sequence 0, 3, 6, 12, 24, 48, 96, each number double the last, added 4 to each, and divided by 10, the resulting numbers closely matched the known planetary distances from the Sun, measured in astronomical units. Mercury at 0.4, Venus at 0.7, Earth at 1.0, Mars at 1.6, Jupiter at 5.2, Saturn at 10.0. The pattern was not perfect, but it was tantalizingly close. There was only one problem. The pattern predicted that something should exist at 2.8 astronomical units between Mars and Jupiter, and nothing was there. The gap haunted astronomers. In 1772, Johann Elert Bode popularized the pattern, and it became known as the Titius-Bode law. In 1781, William Herschel discovered Uranus, and its distance from the Sun, 19.2 astronomical units, matched the prediction of 19.6 almost perfectly. The law seemed validated, and the missing body at 2.8 became an obsession. A group of 24 European astronomers, led by Baron Franz Xaver von Zach, organized themselves into what they called the Celestial Police, a systematic search for the missing planet. They divided the zodiac into 24 sectors, assigned one to each member, and began methodically scanning the sky. But before their search could produce results, someone else beat them to it. On the first night of the 19th century, January 1st, 1801, Giuseppe Piazzi, an Italian monk and astronomer working at the Palermo Observatory in Sicily, was compiling a star catalogue. Methodically recording the positions of stars night after night, he noticed a faint point of light that had moved since the previous evening. Stars do not move against the background sky. Planets do. Comets do. But this object was not where any known planet should be. Over the following weeks, Piazzi tracked the mysterious point of light as it drifted slowly through the constellation Taurus. He measured its position with meticulous care, noting its coordinates each clear night. And as the data accumulated, a picture emerged. The object was orbiting the Sun at a distance of approximately 2.8 astronomical units. It was exactly where the Titius-Bode law predicted a planet should be. Piazzi had found the missing world. He named it Ceres, after the Roman goddess of agriculture and the patron deity of Sicily. The scientific world erupted with excitement. The gap was filled. The law was confirmed. A new planet had been added to the solar system, but the celebration was premature. Within a year and a half, another astronomer, Heinrich Wilhelm Olbers, working in Bremen, Germany, discovered a second object orbiting at nearly the same distance. He called it Pallas. Then Carl Ludwig Harding found Juno in 1804. Then Olbers found Vesta in 1807. The gap between Mars and Jupiter did not contain one planet. It contained many objects. And as telescopes improved throughout the 19th century, the number grew, from 4 to 10 to 20 to 100 to thousands. The gap was not a planet, it was a debris field, a graveyard of small bodies, the remnants of something that had either failed to form or been destroyed in the process of trying. The term asteroid, meaning star-like, because these objects appeared as points of light rather than disks, was coined by William Herschel in 1802 to distinguish these small bodies from the proper planets. It was a demotion. Ceres, Pallas, Juno and Vesta lost their planetary status within a generation of being discovered. They were reclassified as minor bodies, interesting perhaps, but not important, not worlds. It was into this growing catalogue of minor bodies that Hygeia quietly arrived. On the evening of April 12, 1849, the Italian astronomer Annibale de Gasparis was scanning the sky from the Capodimonte Observatory, perched on a hilltop above Naples with a commanding view of the bay below. De Gasparis was a dedicated asteroid hunter, patient, meticulous, and relentless. Over his career, he would discover 9 asteroids in total, more than any other astronomer of his era. But Hygeia was his first major find, and the one that brought him international recognition. On that April night, de Gasparis noticed a faint, slow-moving point of light in the constellation Libra that did not match any known object. He tracked it over the following weeks, carefully measuring its position against the background stars. and calculated its orbit. The new body circled the Sun at a distance of roughly 3.14 astronomical units, firmly within the asteroid belt, but farther from the Sun than Ceres. Its orbital period was about 5.5 Earth years. Its orbit was nearly circular, with a low eccentricity of about 0.115, and its inclination, the tilt of its orbital plane relative to Earth's, was modest, at roughly 3.8 degrees. De Gasparis named his discovery Hygeia after the Greek goddess of health and cleanliness, a daughter of Asclepius, the god of medicine. The name was chosen from classical mythology. Following the convention of the time, it would prove ironic. Hygeia, as future centuries of observation would reveal, is one of the dirtiest-looking objects in the solar system. A world cloaked in a surface so dark it absorbs nearly all the light that falls on it, reflecting back less than the blacktop of a parking lot. For the next 150 years, Hygeia lived in obscurity. It was observed periodically, its orbit refined, its brightness measured. From those brightness measurements, astronomers estimated its size, somewhere around 430 kilometers in diameter, give or take a few tens of kilometers depending on the assumptions used. Its albedo, the fraction of sunlight reflected from its surface, was measured at roughly 0.054 or about 5.4%. That number deserves context. Fresh snow reflects about 80 to 90% of the sunlight that hits it. The full moon reflects roughly 12%. A sunlit concrete sidewalk reflects about 30%. Fresh asphalt on a road reflects 7 to 8%. Hygeia reflects 5.4%. It is darker than pavement, darker than charcoal. If you could stand on its surface, you would see a landscape of near-total blackness. Dark rock stretching to a closed, sharp horizon under a distant, shrunken sun. There would be no atmosphere to scatter light, no haze, no colour. Just rock and void and silence. Spectroscopic observations, analyses of the specific wavelengths of light reflected from Hygeia's surface, revealed that it belongs to a class called C-type asteroids. The C stands for carbonaceous. C-type asteroids are the most common type in the outer asteroid belt, and they are among the most primitive objects in the entire solar system. Their surfaces have remained largely unchanged since they formed 4.6 billion years ago, from the primordial cloud of gas and dust that gave birth to the Sun and everything that orbits it. They are rich in carbon, in complex organic molecules, and in hydrated silicates, minerals like clays and serpentine that contain water locked within their crystal structures. They are, in the most literal sense, fossils. Time capsules from the dawn of the solar system, preserved in the cold vacuum of space for longer than life has existed on Earth. This made Hygeia quietly important to a small but dedicated community of researchers who study the early solar system. As one of the largest C-type bodies in the belt, Hygeia represented a rare opportunity, a window into the chemical conditions that existed in the solar nebula during the first few million years of planetary formation. The carbon in your muscles, the water in your blood, the calcium in your bones, all of these atoms were once part of the same primordial cloud that produced bodies like Hygeia. They were built from the same raw material, forged in the same epochs, scattered from the same source. Studying Hygeia was, in a very real sense, studying the ingredients of life itself. But there was a nagging problem. A problem that had been growing quietly for decades, accumulating evidence like snow piling on a rooftop, and it had to do with the enormous family of asteroids that shared Hygeia's orbit. In the asteroid belt, bodies are grouped into families, clusters of asteroids with similar orbits, similar compositions, and a shared origin. These families are not random associations. They are the forensic evidence of ancient violence. Billions of years ago, a large asteroid was struck by a smaller impactor at high speed. The collision shattered the target, or excavated a massive crater from its surface, and the resulting fragments were launched into nearby orbits. Over the eons, these fragments spread apart slightly, their orbits drifting under the influence of subtle gravitational perturbations and the gentle push of solar radiation. But their orbital elements, their distances from the Sun, the shapes of their orbits, their tilts, remained similar enough to identify them as related. Each family is a set of siblings, shrapnel from the same ancient explosion. The Hygeia family is one of the largest and most populous in the entire belt. It contains more than 6,800 identified members, spread across a vast swath of the outer belt between roughly 3.0 and 3.25 astronomical units from the Sun. All of these asteroids share Hygeia's dark carbonaceous composition. They share similar orbital inclinations, and their sheer number tells a dramatic story. To produce that many fragments, that much material, the impact that created the family had to be spectacularly violent. Models based on the total estimated mass of the family members predicted that the collision should have excavated a crater on Hygeia's surface, at least 200 kilometers in diameter. Some estimates put it even larger. On a body only 430 kilometers wide, such a crater would dominate the entire globe. It would be the single most conspicuous feature on the surface. It would be the first thing anyone saw. But every attempt to observe this crater came up empty. Throughout the 1980s, the 1990s, and the 2000s, astronomers periodically pointed their best instruments at Hygeia and tried to resolve surface features. The data was always frustratingly inconclusive. Hygeia was too far away, too dark, and too small for the telescopes of the era to see clearly. It appeared as nothing more than a smudge of a few blurry pixels, too indistinct to reveal whether a giant crater existed or not. The mystery persisted, unresolved and largely unnoticed by the broader scientific community. And then came 2019 and Spare. The Very Large Telescope sits atop Cerro Paranal, a flattened mountain in the Atacama Desert of northern Chile, at an altitude of 2,635 meters. The Atacama is one of the driest places on Earth. Parts of it have not received measurable rainfall in over 400 years. The soil is so barren that NASA has used it as an analogue for the surface of Mars. The air above it is thin, dry, and extraordinarily stable, conditions that make it one of the finest astronomical observing sites on the planet. On a clear night, which is most nights, the sky above Paranal is so dark and so transparent that the Milky Way casts visible shadows on the ground. The VLT itself is not a single telescope. It is a complex of 4 main telescopes, each equipped with a primary mirror 8.2 meters in diameter, larger than many living rooms. These 4 units can operate independently or be combined through a technique called interferometry, which synthesizes their light to achieve the resolving power of a telescope with a mirror equivalent to the distance between them. The VLT is one of the most powerful optical observatories ever constructed. The instrument that changed Hygeia's story was called SPARE, the Spectropolarimetric High Contrast Exoplanet Research Instrument. SPHERE was designed for one of the most technically demanding tasks in all of astronomy, directly imaging planets around other stars. Exoplanets are millions of times fainter than their host stars, and separated by angles so tiny that they are measured in fractions of an arcsecond. Detecting them requires suppressing the star's overwhelming glare while simultaneously compensating for the blurring effects of Earth's atmosphere. SPARE does this through a combination of adaptive optics, a system that uses a deformable mirror and a wavefront sensor to correct atmospheric distortion in real time, adjusting the mirror's surface more than 1,000 times per second, and a coronagraph which blocks the star's light to reveal faint companions nearby. When Pierre Venazza and his team at the Laboratoire d'Astrophysique de Marseille turned SPARE toward Hygeia in the summer of 2019, they were repurposing the instrument. They were not hunting for exoplanets, they were hunting for a crater. They believed that SPHERE's extraordinary resolution, its ability to discern details as small as 25 kilometers on Hygeia's surface, would finally reveal the giant impact basin that had to be there. They expected confirmation of a prediction. They expected the scar. What they saw instead launched a debate that has not been settled to this day. Hygeia was round, not lumpy, not irregular, not elongated, not potato-shaped, round. The images showed a smooth, dark, nearly featureless globe. The team measured its shape along 3 axes and found dimensions of roughly 450 by 430 by 424 kilometers. Numbers so close to each other that the body is, within measurement uncertainty, a sphere. No giant crater was visible anywhere on the surface, no massive basin, no towering rim. The expected wound was simply absent. Venazza announced the results with careful precision. He told the press that the observations were unexpected and significant. The team had expected a large impact basin and instead found a body whose shape was consistent with hydrostatic equilibrium. And then he delivered the line that made headlines around the world. If Hygeia is indeed in hydrostatic equilibrium, it satisfies all 4 criteria required by the International Astronomical Union for classification as a dwarf planet. The implications began to ripple outward immediately. Hygeia, the dark, silent, overlooked 4th largest body in the asteroid belt, might not be an asteroid at all. It might be a world. And answering that question would require confronting a violent past, a fragile present, and a definition that the scientific community has been arguing about for almost 20 years. But the roundness was only half of the puzzle that Spare had uncovered. The other half was the missing crater, and answering that mystery would require a journey into the physics of destruction and reassembly, processes so violent and so transformative that they challenge our understanding of how worlds are built and what it means for a body to survive. Before we go there, though, it is worth pausing to appreciate the sheer difficulty of what Vanasa's team accomplished. Hygeia, at the time of the Sphere observations, was roughly 3 astronomical units from Earth, about 450 million kilometers. That is roughly 3 times the distance from the Earth to the Sun. At that distance, Hygeia appeared in the sky as a point of light so faint that it was invisible to the naked eye and barely detectable even with a modest amateur telescope. Its apparent diameter on the sky was roughly 0.1 arcseconds, a measurement so small that it is almost impossible to convey in everyday terms. Here is one way to think about it. Hold a coin, any coin, at arm's length. The diameter of that coin, as seen from your eye, subtends an angle of about 1 degree. 1 arcsecond is 1/3600th of a degree, and 0.1 arcseconds is 10 times smaller than that. Seeing Hygeia's shape from Earth is equivalent to reading the date on a coin held by someone standing 30 kilometers away. That is not an exaggeration. That is the actual angular resolution required. Sphere achieved it, from the ground through the turbulent atmosphere, using a mirror smaller than the width of a 2-lane road. The fact that we can resolve the shape of an object 450 million kilometers away, see that it is round, and measure its dimensions to within a few tens of kilometers is itself a testament to the extraordinary capabilities of modern astronomy. A century ago, Hygeia was a dot. 50 years ago, it was a slightly better characterized dot. In 2019, it became a world, or at least a candidate for one. But classification in astronomy is never simple. The International Astronomical Union's definition of a dwarf planet, adopted in 2006, contains 4 criteria. A dwarf planet must orbit the Sun. It must not be a satellite of another body. It must not have cleared the neighborhood around its orbit. And, the critical criterion for Hygeia, it must have sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium shape. That last criterion, hydrostatic equilibrium, sounds straightforward. A body's own gravity pulls it into a sphere. If the body is big enough, gravity wins, and the result is a round shape. If it is too small, the internal strength of the material holds, and the body stays irregular. The threshold between these 2 regimes depends on composition, temperature, and history. But for a typical rocky asteroid, it was thought to be somewhere around 600 to 900 kilometers. Hygeia, at 430 kilometers, is well below that range. It should not be round. The fact that it is round means either the models are wrong, or something unusual happened to Hygeia. Something that bypassed the normal pathway to hydrostatic equilibrium entirely. And that something, as the Spare team and their simulation colleagues would soon demonstrate, was among the most violent events in the history of the asteroid belt. An event that destroyed Hygeia completely, and then, against all odds, put it back together again. The stage was set. The puzzle had 2 pieces, a body that should not be round, and a crater that should exist but does not. The solution would require venturing into the physics of catastrophic disruption, a field where the boundary between creation and destruction is not just blurred, but erased entirely. To grasp the full significance of what happened to Hygeia, it helps to understand and just how much energy is involved in asteroid collisions at the speeds typical of the belt. Objects in the asteroid belt orbit the Sun at velocities of roughly 15 to 25 kilometers per second. But because they orbit in different directions, at different inclinations, and with different eccentricities, their relative velocities, when they meet, are typically 5 to 10 kilometers per second. 5 kilometers per second is about 18,000 kilometers per hour. That is 23 times faster than the speed of sound in air. It is fast enough that the impactor does not push into the target body. It does not dent it or crack it. It explodes into it. The kinetic energy of the collision is converted into heat and shock waves so intense that both the impactor and the target material are vaporized, melted, or shattered at the point of contact. At these speeds, even a modest-sized impactor carries an almost inconceivable amount of energy. The kinetic energy of a moving object is proportional to its mass times the square of its velocity. Double the speed, and the energy quadruples. An impactor 100 kilometers across, traveling at 7 kilometers per second, carries energy roughly equivalent to several billion joules. To put that in perspective, all of human civilization's annual energy consumption, every power plant, every vehicle, every factory, every home on Earth, amounts to roughly 580 billion joules per year. A single asteroid impact in the belt can release energy comparable to what the entire human race uses in a year, in seconds. That is the scale of violence we are dealing with when we talk about the event that destroyed the original Hygeia. Not a crater-forming impact, not a surface wound, a planet-killing explosion delivered to a body that was minding its own business in the cold outer reaches of the asteroid belt by an impactor that arrived at 25,000 kilometers per hour and converted every joule of its kinetic energy into pure destruction. And yet, out of that destruction, something new was born, something round, something that might, depending on how you read a single sentence in a 20-year-old definition, qualify as a world. This is the paradox at the heart of Hygeia's story. The very event that should have ended it, the collision that shattered it to pieces, may be the event that gave it its most planet-like quality. Without the impact, Hygeia would probably be lumpy and irregular, like most asteroids its size. With the impact, it was destroyed, and then rebuilt in a form that is eerily, disturbingly spherical. The violence did not just reshape Hygeia, it remade it, and the thing it made looks, by every measurable standard, like a world. Jupiter ruined everything. 4.6 billion years ago, when the solar system was still young, still assembling itself from the swirling disk of gas and dust that surrounded the infant sun. The region between Mars and Jupiter was not an empty wasteland. It was a construction zone. Millions of small bodies called planetesimals, ranging from pebbles to objects hundreds of kilometers wide, were colliding, sticking together, and growing. This process, known as accretion, is how all the rocky planets were built. Earth started as a cloud of dust. That dust became gravel. The gravel became boulders. The boulders became protoplanets. And the protoplanets, over tens of millions of years of collisions and mergers, became the planet you are standing on right now. The same process was underway between Mars and Jupiter. Given enough time and enough raw material, it should have produced a fifth rocky planet. But Jupiter got there first, and its arrival was a catastrophe from which the asteroid belt has never recovered. Jupiter formed with extraordinary speed. Current models suggest that its core, a lump of rock and ice roughly 10 to 20 times the mass of Earth, assembled within the first few million years of the solar system's existence. That may sound like a long time, but in solar system terms, it is almost instantaneous. The inner planets took tens of millions of years to reach their current sizes. Jupiter's core crossed a critical threshold in a fraction of that time, and once it crossed that threshold, something remarkable happened. Jupiter's core became massive enough for its gravity to capture hydrogen and helium gas directly from the surrounding solar nebula. This triggered a runaway process. The more gas Jupiter captured, the more massive it became. The more massive it became, the stronger its gravity grew. The stronger its gravity grew, the more gas it captured. Within perhaps another million years, Jupiter had ballooned from a rocky core into a gas giant, a monster 318 times the mass of Earth, 11 times its diameter, containing more than twice the material of every other planet in the solar system put together, and its gravitational influence was devastating. Jupiter's enormous mass created a web of gravitational resonances throughout the inner solar system, specific orbital distances where the gravitational perturbations from Jupiter accumulated over time, pumping energy into the orbits of smaller bodies. In the region that would become the asteroid belt, these resonances were fatal to the planet-building process. Here is how it worked. A planetesimal orbiting at a distance, where its orbital period was exactly 1/3 of Jupiter's, would receive a gravitational tug from Jupiter at the same point in its orbit every third lap. These tugs, though individually small, accumulated over millions of orbits. Slowly, inexorably, they stretched the planetesimal's orbit from circular to elliptical. They increased its velocity relative to neighboring objects. And when objects moving at different speeds collide, the results are very different from when slow-moving objects gently bump together. At low speeds, below about 1 meter per second, colliding planetesimals tend to stick. They merge. They grow. This is constructive accretion, and it is how planets are built. But at higher speeds, several hundred meters per second or more, collisions become destructive. The objects shatter on impact. Instead of growing, they fragment. Instead of building a planet, they grind each other to dust. Jupiter's resonances pushed collision velocities in the belt well above the destructive threshold. Objects that should have been gently merging were instead smashing each other apart at kilometers per second. The construction site became a demolition zone, and over the next several 100 million years, Jupiter systematically emptied the belt. Gravitational perturbations ejected roughly 99% of the original material, flinging asteroids into the inner solar system, where they bombarded the young rocky planets, or hurling them outward into the outer solar system, or expelling them from the solar system entirely, lost to interstellar space. What remains today is a ghost of what was. The total mass of the modern asteroid belt is estimated at roughly 3.2 times 10 to the 21st kilograms. That is approximately 4% of the mass of Earth's moon. If you could somehow gather every asteroid in the belt and compress them into a single sphere, you would get a body roughly 1,500 kilometers in diameter, smaller than Pluto, smaller than many of Jupiter's own moons. The belt is not a disrupted planet. It is the faint echo of a planet that was never allowed to be born. Jupiter strangled it in the cradle. Among the survivors of this prolonged cosmic grinding, Hygeia stands out for a reason that goes beyond its size or its darkness. It stands out because of its shape. And to understand why that shape is such a problem, you need to understand the physics of hydrostatic equilibrium at a level that most popular accounts gloss over. Hydrostatic equilibrium is a concept borrowed from fluid mechanics. In a fluid, a liquid or a gas, pressure at any point is determined by the weight of the material above it. At the bottom of the ocean, the pressure is enormous because there is a vast column of water pressing down. At the surface, the pressure is lower. In equilibrium, the pressure at every point exactly balances the gravitational force pulling inward, and the fluid settles into a stable shape. For a self-gravitating body, a body held together by its own gravity, that stable shape is a sphere. But asteroids are not fluids. They are made of rock. Rock is rigid. It has compressive strength, the ability to resist being squeezed, and tensile strength, the ability to resist being pulled apart. A small rock can hold any shape it wants, because the gravitational forces acting on it are far too weak to deform it. A boulder shaped like a dog will stay shaped like a dog for billions of years, because gravity at that scales is negligible compared to the strength of the material. As objects get larger, however, the balance shifts. Gravitational force at the surface of a body increases with its mass, which increases with the cube of the radius. The pressure at the center of the body, the weight of all the material pressing down from above, increases even faster. At some critical size, the pressure at the center exceeds the yield strength of the material. The rock at the center begins to deform. It flows, not like water, but slowly, plastically, like putty squeezed in a fist. Over millions of years, this slow plastic flow reshapes the body, smoothing out irregularities, filling in low spots, leveling high spots, until the body settles into a sphere. This process is called gravitational relaxation, and the critical size at which it begins depends strongly on the material. For ice, which is relatively weak, relaxation can occur at diameters as small as 400 kilometers. The icy moons of Saturn and Uranus provide examples. Mimas, at just 396 kilometers in diameter, is roughly spherical, while Saturn's moon Hyperion, at 270 kilometers, is wildly irregular. The ice allows Mimas to relax into a sphere at a relatively modest size. For rock, the threshold is much higher. Silicate rock is significantly stronger than ice. It resists deformation more effectively. Models predicted that a purely rocky body would need to be at least 600 to 800 kilometers in diameter to achieve hydrostatic equilibrium. Some models put the threshold even higher, above 900 kilometers, depending on the composition and the thermal history of the body. Below that threshold, the rock is too strong for gravity to deform, and the body remains irregular. Hygeia sits far below this threshold. At 430 kilometers, it is roughly half the size that models predict a rocky body would need to be to become spherical through gravitational relaxation alone. And yet it is spherical. This means that one of two things must be true. Either the models are wrong. The threshold for hydrostatic equilibrium in rocky bodies is much lower than we thought, or Hygeia's roundness was not produced by gravitational relaxation at all. It was produced by something else entirely. The SPARE team, in collaboration with a group of impact physicists, proposed the second explanation, and the evidence they presented was compelling, detailed, and deeply unsettling. Their hypothesis, the original Hygeia, was struck by an impactor large enough and fast enough to completely shatter it, not partially disrupt it, not excavate a crater, completely shatter it, reducing the entire body to a cloud of fragments. And then, over a timescale of hours to days, the fragments fell back together under their mutual gravity, reassembling into a new body. That new body, the Hygeia we see today, was spherical, not because gravity slowly crushed it into a sphere over billions of years, but because the reaccumulation process naturally produces a spherical shape when fragments fall inward from all directions. To test this hypothesis, the team ran a massive suite of numerical simulations using a technique called smooth particle hydrodynamics, or SPH. In SPH simulations, the bodies involved in the collision are represented not as solid objects, but as collections of thousands or millions of computational particles, each carrying information about mass, velocity, pressure, temperature, and material properties. The simulation calculates how these particles interact, through gravity, through pressure, through shock waves, and tracks their evolution over time. The team ran more than 100 separate simulations, systematically varying the key parameters, the size of the impactor ranging from 50 to 200 kilometers, the speed of the collision ranging from 5 to 10 kilometers per second, the angle of impact from head-on to highly oblique, and the internal structure of the target from monolithic rock to pre-fractured rubble. The results that best matched the observed properties of Hygeia and its family shared a common narrative. The impactor was roughly 75 to 150 kilometers in diameter. It struck at a velocity of about 7 kilometers per second, and the collision was energetic enough to completely disrupt the target, to fragment it into billions of pieces, from dust grains to chunks kilometers across. In the simulations, the debris cloud expanded outward for a period of hours, reaching a maximum radius several times larger than the original body. Then, as the fragment's outward velocities bled away under the collective gravitational pull of the cloud, the expansion slowed, stopped, and reversed. The cloud began to collapse. The largest fragments attracted the smaller ones. Collisions within the collapsing cloud dissipated kinetic energy, causing the material to settle and compact. Over a period of roughly 12 to 24 hours, the cloud collapsed into a single, roughly spherical body that contained about 80 to 90% of the original mass. The remaining 10 to 20% escaped as smaller fragments, becoming the Hygeia family. The numbers are striking. More than 6,000 known asteroids, the entire Hygeia family, are the leftover crumbs of this reconstruction. They are the pieces that did not make it back. They are the debris that escaped the gravitational pull of the reassembling body, and went on to orbit the Sun independently. Every one of them is a fragment of the original Hygeia. Every one of them is evidence of the violence that created the Hygeia we see today. And the new body, the reassembled Hygeia, emerged from this process with a shape that was startlingly round. In the simulations, the reaccumulated body was consistently spherical, regardless of the exact impact parameters. This makes physical sense. When a cloud of debris collapses under its own gravity, the collapse is roughly symmetric. Material falls inward from all directions, converging toward the center of mass. The resulting body takes the shape imposed by gravitational symmetry, a sphere. But here is the critical question, the one that has divided the planetary science community since 2019. Is this sphere truly in hydrostatic equilibrium? Or is it simply a shape, a snapshot, frozen in place by the rigidity of the reaccumulated rubble? The distinction matters enormously. If Hygeia is in genuine hydrostatic equilibrium, if its gravity is actively maintaining its shape against internal stresses, in the same way that Earth's gravity maintains Earth's shape, then it meets the IAU's criterion for dwarf planet status, and it should be reclassified. But if Hygeia is merely a rubble pile that fell together in a round shape and has been sitting there, inert, ever since, its shape a fossil of the reaccumulation process rather than an ongoing physical state, then it does not meet the criterion, regardless of how spherical it looks. The problem is that we cannot tell the difference from a photograph. A sphere is a sphere. You cannot look at a round body from 450 million kilometers away and determine whether its roundness is maintained by active gravitational equilibrium or by the passive structural strength of compacted rubble. You would need to measure its internal structure, its density profile, its rigidity, its response to tidal forces. You would need, in short, to send a spacecraft. And no spacecraft has ever visited Hygeia. This uncertainty is what makes the Hygeia debate so persistent and so contentious. The data we have, the spare images, tell us that Hygeia is round. The simulations tell us how it probably got that way. But neither the data nor the simulations can answer the fundamental question. Is Hygeia a world? The answer depends on a definition. And that definition, as the entire planetary science community has learned over the past 2 decades, is anything but settled. In 2006, the International Astronomical Union convened a meeting in Prague that would produce the most famous and most divisive decision in the history of modern astronomy. The subject was Pluto. For 76 years, since Clyde Tombaugh's discovery in 1930, Pluto had been the 9th planet. But the discovery of increasingly large objects in the Kuiper Belt, the vast ring of icy bodies beyond Neptune, had forced a reckoning. The crisis reached its peak in 2005, when Mike Brown and his team at the California Institute of Technology announced the discovery of Eris, an object in the scattered disk beyond the Kuiper Belt that appeared to be larger than Pluto. If Pluto was a planet, then Eris was a planet too, and Makemake, and Haumea, and potentially dozens or even hundreds more, as our surveys of the outer solar system continued to discover new bodies. The choice was stark: either accept a solar system with dozens of planets and a number that would keep growing, or redefine what a planet is. The IAU chose to redefine. Resolution 5A, adopted on August 24, 2006, established 3 requirements for planehood. First, the body must orbit the Sun. Second, it must have sufficient mass for its self-gravity to overcome rigid body forces, so that it assumes a hydrostatic equilibrium shape. In plain language, it must be round. Third, it must have cleared the neighbourhood around its orbit. Pluto met the first 2 criteria, but failed the third. It shares its orbital neighbourhood with thousands of other Kuiper Belt objects. It has not gravitationally dominated its region of space. And so, by a vote of a few hundred astronomers out of more than 10,000 IAU members worldwide, Pluto was reclassified from planet to dwarf planet, a new category created specifically to contain it. The vote was met with fury from some quarters. Alan Stern, the principal investigator of NASA's New Horizons mission to Pluto, condemned the decision publicly and repeatedly. He called it sloppy science. He pointed out that the clearing the orbit criterion was not a property of the body itself, but a function of its distance from the Sun. A body the mass of Earth if placed in the Kuiper belt, would not have cleared its orbit either. The region is too vast and too populated. By the IAU's logic, Earth would not be a planet if it orbited at 40 astronomical units instead of 1. That, Stern argued, was absurd. Nearly 2 decades later, the debate remains unresolved. And Hygeia has added a new dimension to it, because Hygeia does not just fail the orbit-clearing criterion. Like Pluto, it shares its orbital space with thousands of other asteroids. Hygeia challenges the second criterion itself, the requirement for hydrostatic equilibrium. It is round, but perhaps not in the way the IAU intended. Its roundness may be an artifact of destruction rather than a signature of gravitational dominance. And yet, if you read the IAU's words strictly, sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium shape, Hygeia fits. Its self-gravity did overcome rigid body forces. The reassembly was driven by gravity. The resulting shape is consistent with equilibrium. The words do not specify how long the process must take, or whether it must be the body's original formation process. They simply describe an end state. But here is what makes this truly terrifying. The Hygeia question is not just about one asteroid, it is about the boundary between categories that we have treated as self-evident for centuries. Planet, asteroid, rock, world. We assumed these categories were clear. We assumed that the universe would cooperate with our need to organize it into neat boxes. Hygeia is evidence that it will not. The universe does not care about our definitions. It builds what it builds, destroys what it destroys, and reassembles the pieces in whatever shape gravity dictates. Whether we call the result a planet, a dwarf planet, or a very round asteroid is entirely our problem. The universe has already moved on. And this brings us to perhaps the most unsettling dimension of the Hygeia problem, the question of what lies beneath the surface. Because the debate over Hygeia's classification is not just about shape, it is about substance. And the substance of Hygeia, its interior, its density, its structural integrity, raises questions that the sphere images alone cannot answer. Hygeia's average density has been measured at roughly 2.06 grams per cubic centimeter. That number sounds abstract, so let us put it in context. Water has a density of 1 gram per cubic centimeter. Ordinary granite has a density of about 2.7. Iron has a density of about 7.9. Earth as a whole has an average density of 5.5 grams per cubic centimeter, a number that reflects its massive iron core. Hygeia's density of 2.06 is strikingly low for a body of its size. It is only slightly more than twice the density of water. This low density can be explained in one of two ways, and both of them tell us something profound about Hygeia's nature. The first explanation is compositional. Hygeia might simply be made of inherently low-density material, a mixture of carbonaceous rock and a significant fraction of water ice or hydrated minerals. C-type asteroids are known to contain hydrated silicates, minerals that have water molecules trapped within their crystal lattices. If Hygeia contains a substantial amount of these minerals, or if it retains pockets of water ice in its interior, its bulk density could be low without requiring any unusual internal structure. This interpretation would make Hygeia a water-rich world, a body that may have played a role, billions of years ago, in delivering water and organic material to the inner solar system and potentially to Earth itself. The second explanation is structural. Hygeia might be porous, riddled with internal voids, gaps, and fractures that reduce its overall density below what solid rock would produce. This is what you would expect from a rubble pile. If Hygeia was shattered and reassembled, the reassembly process would not have produced a perfectly compacted body. There would be spaces between the fragments, gaps where the pieces did not fit together perfectly, cavities sealed beneath the surface, structural weaknesses threading through the interior like cracks in old plaster. A body like this would be fundamentally fragile, not held together by the strength of solid rock, but by the weak, diffuse pull of its own modest gravity, like a pile of gravel that happens to be round. The truth is probably a combination of both factors. Hygeia likely contains some fraction of water ice or hydrated minerals, giving it a naturally low bulk composition density, and it likely has some degree of internal porosity, reflecting its violent history of disruption and reassembly, but the exact proportions are unknown. Without a spacecraft in orbit around Hygiea, without gravity field measurements, without seismic data, without close-up imaging of the surface texture, we cannot determine its internal structure with confidence. And this uncertainty has enormous implications for the classification debate. If Hygiea is mostly solid with a low-density composition but a compact internal structure, then its gravity is genuinely maintaining its spherical shape, and it may truly be in hydrostatic equilibrium. But if Hygiea is highly porous, if its interior is more empty space than solid rock, then its spherical shape may not reflect active gravitational equilibrium at all. It may simply be the shape in which the rubble came to rest, frozen in place by friction and compaction, not sustained by gravitational force. Imagine building a sand castle in the shape of a perfect sphere. You could do it with enough patience and a spherical mold. The result would look round. It would even resist small perturbations, but it would not be in hydrostatic equilibrium. It would be a shape held together by friction between grains, not by gravity. Push hard enough, and it would crumble. Hygiea might be the cosmic equivalent, a round shape without a round reason. Or it might not. It might be genuinely round for genuine physical reasons. Its gravity, modest though it is, might be sufficient to maintain its shape against all the perturbations it has experienced over billions of years of existence in the asteroid belt. We simply do not know. And the inability to distinguish between these two scenarios, given our current data, is what makes the Hygiea debate so frustrating and so fascinating. There is another dimension to the mystery that deserves attention, and it concerns the surface itself. The Spear images, while revolutionary, had a resolution of roughly 25 kilometers pixel. That is good enough to determine the overall shape of the body and to confirm the absence of a truly massive crater. But it is not good enough to see small-scale features. Craters smaller than 25 kilometers, hills, ridges, fracture networks, color variations, compositional boundaries, all of these are invisible at Sphere's resolution. Earlier ground-based observations using adaptive optics systems on other large telescopes had provided some constraints on Hygiea's surface features. Light curve measurements, observations of how Hygiea's brightness changes as it rotates, had been used to estimate its rotation period at roughly 27.6 hours. That is a slow rotation, longer than Earth's 24-hour day. The light curve also showed very small amplitude variations, suggesting that Hygiea's shape is close to symmetric, consistent with a sphere, but not uniquely diagnostic. Thermal observations, measurements of the infrared radiation emitted by Hygiea as it cools during its rotation, provided information about its surface properties. Hygiea's surface appears to be covered in a layer of fine-grained regolith, a blanket of dust and small fragments produced by billions of years of micrometeorite bombardment. This regolith acts as an insulating layer, trapping heat during the day and releasing it slowly during the night. The thermal inertia of Hygiea's surface is low, consistent with a loose, powdery surface rather than solid bedrock. All of this is consistent with the rubble pile hypothesis. A body that was shattered and reassembled would naturally develop a regolith-covered surface. The reassembly process itself would produce a surface of loose fragments, and subsequent bombardment by small impactors would grind those fragments into finer and finer particles over time. The result would be a world coated in dark, fine-grained dust, exactly what we observe. But the real test of Hygiea's nature will require a spacecraft, and as of now, no mission to Hygiea has been approved, funded, or even seriously proposed by any space agency. The European Space Agency's Hera mission, launched in 2024, is designed to study the binary asteroid Didymos and its moon Dimorphos, the target of NASA's DART impact test. NASA's Lucy mission is visiting Jupiter's Trojan asteroids, objects that share Jupiter's orbit, leading and trailing the giant planet by 60 degrees. NASA's Psyche mission is en route to the metallic asteroid Psyche, which may be the exposed iron core of a shattered protoplanet. None of these missions will visit Hygiea. The reasons are practical. Hygiea orbits in the outer asteroid belt, roughly 3 astronomical units from the Sun. It is farther away and harder to reach than many other targets. Its dark surface makes it difficult to study, even from close range. There is very little reflected light to work with. And perhaps most importantly, it has never generated the public excitement that drives mission funding. Ceres has its bright spots and its subsurface ocean. Vesta has its enormous impact craters and its connection to meteorites on Earth. Psyche has its iron surface and the tantalizing possibility of being a planetary core. Hygeia has, what? A dark surface, a round shape, a missing crater? The irony is bitter. The very qualities that make Hygeia scientifically extraordinary, its paradoxical roundness, its violent rebirth, its position at the boundary of planetary definition, are the same qualities that make it a hard sell to the public and to funding agencies. It is not shiny, it is not dramatic in photographs, it does not have a catchy hook beyond, it might be a dwarf planet depending on how you read the definition, and so it waits. Dark, round, silent, orbiting the Sun at 3 astronomical units, keeping its secrets, while the scientific community argues about what to call it. But the questions Hygeia raises will not wait. They are growing more urgent with every new discovery. Because Hygeia is not the only body in the solar system that challenges our definitions. It is not the only object that sits on the boundary between categories. And the more we explore, the more we survey, the more we measure, the more of these boundary objects we find. The neat, clean categories that we drew up in 2006, planet, dwarf planet, small solar system body, are leaking at every seam. And Hygeia, sitting quietly in the dark, is one of the biggest leaks of all. Consider the broader landscape. In the Kuiper Belt, the ring of icy bodies beyond Neptune, astronomers have identified dozens of objects large enough to potentially be in hydrostatic equilibrium. Some of them, like Sedna and Quar, have estimated diameters that place them near the threshold. Others, like Gong and Orcus, have been measured with enough precision to suggest spherical or near-spherical shapes. Each one is a potential dwarf planet. Each one is a potential reclassification. And each one carries its own version of the same question: how round is round enough? The problem is not limited to the outer solar system. In the asteroid belt itself, there are objects that challenge the categories in other ways. Ceres, the only currently recognized dwarf planet in the belt, has a subsurface ocean of liquid brine, a feature more commonly associated with the icy moons of Jupiter and Saturn. If Ceres has an ocean, it shares a fundamental characteristic with bodies like Europa and Enceladus, which are not dwarf planets but moons. Does the presence of an ocean change what category a body belongs in? The IAU definition says no. It is only about shape, orbit, and orbital dominance. But many scientists argue that the IAU definition is far too narrow, that it ignores the geophysical properties that actually make a body interesting and scientifically important. Philip Metzger, a planetary physicist at the University of Central Florida, published a study in 2019, the same year as the Hygeia observations, in which he reviewed more than 200 years of scientific literature and concluded that the concept of clearing the orbit was used as a criterion for planehood exactly once in history, in the IAU's 2006 resolution. Before that, no scientist had ever used orbital dominance as a definitional criterion. The historical practice, Metzger argued, was always geophysical. A planet was defined by what it was, not by where it was. The IAU resolution, in his view, was an anomaly, and a damaging one. This is the scientific landscape into which Hygeia's roundness erupted. A community already divided over the Pluto decision, a definition already under assault from multiple directions. And now, a new data point, a body that is the wrong size to be round but is round anyway, that was destroyed and rebuilt, that satisfies the letter of the IAU's criteria but perhaps not the spirit, and that forces everyone involved to confront the uncomfortable reality that nature does not organize itself for our convenience. Hygeia is not the first time the solar system has forced astronomers to revise their categories. When Ceres was discovered in 1801, it was called a planet. When more asteroids were found, it was demoted to a minor body. When the IAU created the dwarf planet category in 2006, Ceres was promoted again. Pluto went from planet to dwarf planet. The solar system's boundaries have been redrawn repeatedly, and each redrawing has been contentious, emotional, and deeply personal for the scientists involved. But Hygeia's case adds a dimension that previous debates lacked. It introduces the question of history. Previous classification debates were about intrinsic properties, size, shape, orbit, measured at the present moment. Hygeia's debate is about process, how a body achieved its shape, whether the pathway to roundness matters as much as the roundness itself. Whether a world that was destroyed and rebuilt counts as the same kind of thing as a world that has been round since birth. There is no consensus. There may never be one, and that in a strange way is what makes Hygeia so important. It is not important because it is large or bright or spectacular. It is important because it is ambiguous, because it sits exactly on the line that we have drawn, and it refuses to stand on either side, because it forces us to ask questions that do not have clean answers, and because the discomfort of not knowing, of sitting with ambiguity, of accepting that our categories are human inventions imposed on a universe that did not ask for them, is itself a kind of knowledge. Something is wrong with our assumptions. Not wrong in the sense that the science is bad. The observations are exquisite. The simulations are rigorous. The measurements are precise. What is wrong is the assumption that the universe has a clean boundary between world and not a world. Hygeia is proof that it does not. The boundary is a blur, a gradient, a spectrum, and somewhere on that spectrum, a dark, round, silent body orbits the sun, waiting patiently for us to figure out what it is. And perhaps the deepest irony of all is that the technology that revealed Hygeia's true nature was not even designed for this purpose. Spare was built to find exoplanets, worlds orbiting other stars, separated from us by light years of empty space. It was designed to peer across distances so vast that they defy comprehension, to separate the faint glow of a distant world from the overwhelming blaze of its parent star. The fact that this same instrument was then turned inward, aimed at a body within our own solar system, and revealed something that decades of prior observation had missed. That is a story about the nature of discovery itself. Discovery is rarely a straight line. The most important findings in science are often accidental, or at least unexpected. Piazzi was not looking for asteroids when he found Ceres. He was cataloguing stars. Hubble was not looking for the expanding universe when he measured galactic redshifts. He was trying to determine distances. Penzias and Wilson were not looking for the cosmic microwave background when they detected it in 1965. They were trying to eliminate an annoying hum in their radio antenna, and Van Allen was not looking for a dwarf planet when he pointed Spare at Hygeia. He was looking for a crater. The crater was not there, but what he found instead may prove to be far more important than a scar on the surface of a minor body. He found a question about what counts as a world, a question about how destruction can create something new, a question about the limits of our categories and the stubbornness of nature in refusing to respect them. And that question, as questions tend to do in science, has opened doors to rooms that no one knew existed. Because if Hygeia can be round at 430 kilometers, whether through reassembly or through some mechanism we have not yet understood, then the hydrostatic equilibrium threshold that we have been teaching in textbooks for decades may be wrong. And if that threshold is wrong, then the number of objects in the solar system that might qualify as dwarf planets is not 5 or 10 or 20. It could be dozens, hundreds. The solar system might be full of worlds, small, dark, overlooked, scattered across the asteroid belt and the Kuiper belt and the scattered disk and the Oort cloud, that we have been calling rocks because we never looked closely enough to see their roundness. That thought is exhilarating and terrifying in equal measure. Exhilarating because it suggests a solar system far richer, far more diverse, far more populated with worlds than we ever imagined. Terrifying because it means that the clean, simple map of the solar system that we all learned in school, 8 planets, a handful of dwarf planets, and a lot of debris, may be nothing more than a cartoon, a simplified sketch of something far more complex, far more nuanced, far more difficult to categorize than our neat labels can accommodate. Hygeia, quiet and dark in its distant orbit, is a messenger from that more complex reality, and the message it carries, etched in its impossible roundness, its missing crater, its violent rebirth, is simple but profound. The universe is not as tidy as we would like it to be. The lines we draw are our own, and the things we choose not to see, the worlds we choose not to name, are not made less real by our indifference. There is one more aspect of Hygeia's story that bears mentioning before we move deeper into the specific attempts that scientists have made to understand it. And it concerns time. Hygeia's rotation period, the time it takes to spin once on its axis, is approximately 27.6 hours. That is longer than Earth's day, but not dramatically so. If you could stand on Hygeia's surface and watch the stars wheel overhead, they would move at a pace that would feel almost familiar. A sunrise, or rather a sunrise, since there is no atmosphere to create the colours and drama of an earthly dawn, would occur roughly every 28 hours. The sun would appear as a bright but distant star, roughly 9 times farther away than it appears from Earth, and it would provide only about 1/9 as much light and heat. The temperature on Hygeia's surface, in the scant sunlight of the outer belt, hovers around -160 degrees Celsius. Cold enough to freeze carbon dioxide, cold enough to make nitrogen a solid, cold enough that water ice, if it exists on the surface, is as hard as granite and about as likely to melt as the bedrock beneath it. In that cold, in that dark, under that distant sun, Hygeia has been orbiting for billions of years. It has outlasted entire geological eras on Earth. It predates the dinosaurs by billions of years. It predates the first cells. It may predate the formation of Earth's oceans. And during all that time, it has kept its secrets, hidden behind its darkness, its distance, and its lack of anything that our instruments could latch onto, until a single night in 2019, when the right telescope, with the right instrument, pointed in the right direction, and saw something that should not have been there. A sphere, a world, a question. The story of Hygeia cannot be told in isolation. It is woven into a much larger tapestry. The story of how scientists have attempted to understand the small bodies of the solar system, how our tools and theories have evolved, and how each new discovery has revealed that the asteroid belt is stranger, more violent, and more dynamic than anyone imagined. To understand what Hygeia is, you need to understand the 5 key chapters in that larger story. 5 attempts, 5 missions, 5 breakthroughs that, one by one, built the foundation on which the Hygeia revelation stands. The first chapter begins with a spacecraft called Dawn. In September of 2007, a spacecraft no larger than a school bus lifted off from Cape Canaveral, Florida, atop a Delta II Heavy rocket, and began a journey that would take it to 2 of the largest objects in the asteroid belt. Its name was Dawn, and its mission was unprecedented. No spacecraft had ever orbited 2 separate bodies in the asteroid belt. No spacecraft had ever used ion propulsion, a slow, patient, almost whisper-quiet engine, to navigate between 2 targets separated by hundreds of millions of kilometers. Dawn was an experiment in endurance, in patience, and in the kind of science that requires years of silent coasting through the void before anything happens at all. Dawn's first target was Vesta. It arrived in July of 2011, after a journey of nearly 4 years, and settled into orbit around the irregularly shaped body. What it found surprised everyone. Vesta was not a dead, featureless lump. It was a protoplanet, a body that had begun the process of differentiating into a layered structure, like Earth, before its growth was arrested by Jupiter's gravitational interference. Dawn's instruments revealed a metallic iron-nickel core, a rocky mantle, and a basaltic crust. Vesta had internal heat. It had volcanism early in its history. It had a geological story to tell. And it had scars. The Rheasilvia impact basin, centered near the South Pole, was staggering. 505 kilometers in diameter and 19 kilometers deep. It was one of the largest impact structures in the entire solar system, and it had been carved out of a body only 525 kilometers wide. The impact that formed it had been catastrophic. It had excavated roughly 1% of Vesta's total volume, launching a plume of debris across the solar system. Some of those fragments had eventually fallen to Earth as Head meteorites, Howardites, Eucrites, and Diogenites, providing scientists with actual physical samples of Vesta's crust and mantle, delivered free of charge across hundreds of millions of kilometers of space. But here is the detail that matters for Hygeia's story. Despite the violence of the Rheasilvia impact, Vesta survived. It was not shattered. It was not disrupted. The impact excavated a crater, sent debris flying, and left a massive scar on the surface. But the body itself remained intact. Its interior structure was preserved. Its layers were not scrambled. It was wounded, but it was not destroyed. Hygeia's experience, according to the simulations, was fundamentally different. The impact that struck Hygeia was not a surface event. It was total disruption. The entire body was fragmented. Every layer, every structure, every feature was obliterated, and then the pieces fell back together. The contrast between Vesta and Hygeia illustrates a critical threshold in impact physics, the boundary between a crater-forming impact and a catastrophically disruptive one. Vesta's impact was on one side of that boundary, Hygeia's was on the other, and the consequences were radically different. Dawn spent 14 months at Vesta before firing its ion engine and departing for Ceres, arriving in March of 2015. And what it found there opened yet another chapter in the story of the asteroid belt, one that has direct implications for how we think about Hygeia. Ceres, from a distance, looked like a heavily cratered, nondescript grey sphere, but as Dawn descended into closer orbits, details emerged that no one had predicted. Bright spots, clusters of highly reflective material, dotted the surface, most prominently inside the Occulta crater. For months, these bright spots were the most discussed mystery in planetary science. Were they ice, salt, something else entirely? The answer, when it came, was sodium carbonate, a type of salt deposited by briny water that had welled up from beneath the surface and then evaporated in the vacuum of space, leaving behind a crust of white mineral residue. The implications were profound. Ceres had liquid water beneath its surface, not in the distant past, but recently and possibly still. The brine that produced the bright spots in Occulta crater had reached the surface within the last few million years, and possibly within the last few thousand. Ceres was not a dead rock. It was an active world, with a subsurface ocean of salty water that could still be erupting onto the surface today. This discovery transformed our understanding of what small bodies in the asteroid belt could be. Before Dawn, the belt was thought to be a collection of dry, dead, geologically inert rocks, interesting for their orbital dynamics and their connection to meteorites, but not for their internal complexity. Ceres shattered that assumption. If a body in the asteroid belt could have a subsurface ocean, then the belt was not just a graveyard. It was a place where water existed, where chemistry happened, where conditions relevant to the origin of life might persist even now. And this raised a question about Hygeia. Hygeia is a C-type asteroid, the same broad compositional class as Ceres. It is rich in hydrated minerals, in carbon compounds, in the kinds of materials that, in Ceres's case, are associated with a water-rich interior. Could Hygeia also contain water? Could its low density, 2.06 grams per cubic centimeter, barely more than twice the density of water, reflect not just porosity from reassembly, but a genuine water-ice component in its interior? The question remains unanswered. But the Dawn mission taught us that the possibilities in the asteroid belt are far wider than we assumed. And that lesson applies directly to Hygeia. The second chapter in this story takes us to a very different kind of mission, one that studied asteroids not by visiting them, but by catching pieces of them and bringing them home. On December 6, 2020, a small capsule entered Earth's atmosphere over the Australian outback at a speed of roughly 12 kilometers per second. It was the sample return capsule from Hayabusa 2, a Japanese spacecraft that had spent more than a year orbiting and studying the asteroid Ryugu, a small, dark, diamond-shaped body roughly 900 meters in diameter. Inside the capsule was approximately 5.4 grams of material scooped from Ryugu's surface and subsurface, less than a teaspoon. But those few grams would prove to be among the most scientifically valuable materials ever collected. Ryugu is a C-type asteroid, the same compositional class as Hygeia, but vastly smaller. It is a rubble pile, a loosely bound collection of fragments held together by gravity alone. Its density is only 1.19 grams per cubic centimeter, barely denser than water, which implies a porosity of more than 50%. More than half of Ryugu is empty space. It is less a solid body and more a gravitationally bound cloud of pebbles and dust. The samples returned by Hayabusa 2 were analysed in laboratories around the world, and the results were extraordinary. The material was rich in water-bearing minerals, phyllosilicates, and other hydrated compounds that contained water locked within their crystal structures. It contained amino acids, the building blocks of proteins, the molecular components of life. It contained complex organic molecules that had formed through chemical processes in the primordial solar nebula 4.6 billion years ago, and had been preserved, unchanged, in the cold darkness of space ever since. This is not science fiction. These are not theoretical possibilities. These are measured, verified, peer-reviewed results from actual samples of an actual asteroid. And they tell us something remarkable about the C-type asteroids as a class. The class to which Hygiea belongs. C-type asteroids are not just rocks. They are repositories of water and organic chemistry. They are delivery vehicles that in the early solar system rained water and carbon compounds onto the surfaces of the young rocky planets. They may have contributed a significant fraction of Earth's water. They may have seeded the chemical building blocks from which life eventually emerged. And Hygiea, at 430 kilometers, is one of the largest such repositories still existing in the inner solar system. The Hayabusa 2 results also shed light on the rubble pile question. Ryugu's extremely low density and high porosity confirm that small asteroids in this class are not solid bodies. They are aggregate structures, collections of fragments held together by gravity and friction, with substantial internal void space. If Hygiea was indeed destroyed and reassembled, as the SPH simulations suggest, then it too is likely a rubble pile, albeit a vastly larger and more massive one. Ryugu is 900 meters across. Hygiea is 430 kilometers across, nearly 500 times larger. But the principle is the same, a body held together by gravity, not by the structural strength of solid rock. The third chapter involves a mission that is still underway as these words are spoken, and it is aimed at some of the most mysterious objects in the solar system. In October of 2021, NASA launched the Lucy spacecraft from Cape Canaveral on a 12-year mission to visit 8 different asteroids, 1 in the main belt and 7 in the Trojan swarms of Jupiter. The Trojans are 2 groups of asteroids that share Jupiter's orbit, locked in gravitational equilibrium at points 60 degrees ahead of and behind the giant planet. These points, called Lagrange points, are gravitational sweet spots where the combined pull of Jupiter and the Sun creates stable zones where small bodies can accumulate over billions of years. The Trojan asteroids are thought to be among the most primitive objects in the solar system, relics of the outer solar nebula, captured into Jupiter's orbit during the chaotic period of planetary migration that reshuffled the solar system's architecture roughly 4 billion years ago. Their compositions are expected to be diverse, including C-type, D-type, and P-type asteroids, all of which are dark, carbon-rich, and potentially water-bearing. Lucy's relevance to the Hygiea story lies in what it will teach us about the diversity of small body shapes, compositions, and internal structures. Every asteroid Lucy visits will add a data point to our understanding of how small bodies are built, how they are destroyed, and how they are reassembled after catastrophic impacts. And every data point will help refine the models that we use to understand bodies like Hygiea. In April of 2025, Lucy made its first asteroid encounter, flying past the main belt asteroid Dinkinesh, a small body roughly 790 meters across, and it found a surprise. Dinkinesh had a moon, a contact binary, 2 smaller asteroids stuck together in a peanut shape, orbiting the main body. The discovery confirmed that the physics of small body interactions, collisions, gravitational capture, tidal disruption, and reassembly, is even more complex than models had assumed. If a body 790 meters across can have a contact binary moon, then the range of possible configurations and histories for small solar system bodies is enormous, and that range has implications for how we interpret Hygiea's story. The 4th chapter takes us back to the asteroid belt and to a body that is, in many ways, Hygiea's mirror image, a large asteroid whose catastrophic past is written all over its surface, in contrast to Hygiea's eerily clean face. The asteroid Psyche, located in the main asteroid belt at a distance of roughly 2.9 astronomical units from the Sun, is one of the most unusual objects in the solar system. Its surface appears to be made almost entirely of metal, iron and nickel, primarily, with little to no silicate rock. This makes it unique among known large asteroids. The leading hypothesis is that Psyche is the exposed iron core of a protoplanet, a body that, early in the solar system's history, was large enough to differentiate into a layered structure with a metallic core and a rocky mantle, like Earth. And then, through one or more catastrophic impacts, the rocky mantle was stripped away, leaving only the core behind. NASA's Psyche spacecraft, launched in October of 2023, is currently en route to this body and is expected to arrive in August of 2029. If the metallic core hypothesis is correct, then Psyche represents a fundamentally different outcome of catastrophic disruption than Hygeia. Psyche was disrupted, but only partially. The mantle was stripped away, but the core survived intact. The remaining body is not a rubble pile. It is a coherent, solid, metallic mass, perhaps the densest large asteroid in the belt. Compare this with Hygeia. Hygeia was also disrupted, but completely. Its entire structure was fragmented and reassembled. Unlike Psyche, whose disruption left behind a coherent remnant, Hygeia's disruption left behind nothing. The body that exists today was built from scratch, from the rubble of the old one. Two catastrophic impacts, two completely different outcomes. One left a naked iron core, the other left a smooth, dark sphere of reaccumulated debris. The difference lies in the details of the impact, the speed, the angle, the energy, the ratio of the impactor's mass to the target's mass. These parameters determine whether a collision strips away outer layers while preserving the core, or whether it shatters the entire body into fragments too small for any single piece to dominate. Hygeia's impact was in the second category. The energy was sufficient for total disruption. Nothing survived from the original body except the fragments themselves, which then fell back together into something new. Understanding the full range of catastrophic impact outcomes, from partial stripping to total disruption to rubble pile reassembly, is one of the central goals of asteroid science in the 21st century, and Hygeia sits at one extreme of that range, a body whose entire structure is a consequence of its own destruction. The fifth and final chapter in this story of exploration and attempted understanding brings us to the most direct experiment ever conducted on an asteroid, one that took place not through observation or sampling, but through deliberate destruction. On September 26, 2022, NASA's DART spacecraft, the Double Asteroid Redirection Test, slammed into Dimorphos, the small moonlet orbiting the asteroid Didymos, at a speed of roughly 6.1 kilometers per second. DART's mission was not scientific curiosity, it was planetary defense. The goal was to determine whether a kinetic impactor, a spacecraft deliberately crashed into an asteroid, could change the asteroid's orbit enough to protect Earth from a future impact threat. The impact was spectacular. A plume of debris erupted from Dimorphos' surface, streaming outward in a bright fan of ejected material that was visible to telescopes on Earth for weeks. The Moon's orbital period around Didymos decreased by 33 minutes, far more than the models had predicted, and the reason for this surprisingly large change was directly relevant to the Hygeia story. Dimorphos, like Ryugu, is a rubble pile. Its surface is not solid bedrock. It is a loose collection of boulders, cobbles, and finer material held together by gravity alone. When DART struck, the impact did not create a simple crater in solid rock. It excavated a massive volume of loose material, launching it outward at speeds high enough to escape Dimorphos' feeble gravity. This ejected material, the ejector, carried momentum with it, and the recoil from that momentum transfer amplified the effect of the impact far beyond what the spacecraft's own mass and velocity would have produced. The ejector acted like a rocket engine, pushing Dimorphos in the opposite direction and changing its orbit more than the direct impact alone would have accomplished. The DART experiment demonstrated a fundamental truth about rubble pile asteroids. They respond to impacts very differently than solid bodies do. They are easier to disrupt. They eject more material. They transfer more momentum. And they are, in a very real sense, more fragile. Now apply that insight to Hygeia. If Hygeia was a rubble pile before the catastrophic impact, or if it became one during the impact, then the dynamics of its destruction and reassembly would have been governed by the same physics that DART illuminated on Dimorphos. The ejector would have carried away significant momentum. The fragmentation would have been thorough and complete, and the reassembly, the gravitational collapse of the debris cloud back into a single body, would have produced exactly the kind of smooth, spherical rubble pile that the spare images show. DART was not designed to answer questions about Hygeia. but the physics is the same. The insights transfer directly, and they reinforce the picture that has been building throughout this chapter. A picture of asteroids not as simple, static rocks, but as dynamic, fragile, complex objects with violent histories and uncertain futures. Taken together, these 5 chapters, Dawn's revelation of Vesta's and Ceres's complexity, Hayabusa 2's confirmation of C-type asteroids as water and organics-rich rubble piles, Lucy's ongoing survey of Trojan diversity, the Psyche mission's investigation of catastrophic stripping, and DART's direct experiment with rubble pile physics form the scientific foundation on which our understanding of Hygeia rests. Each mission, each discovery, each experiment has added a piece to the puzzle, and the picture that is emerging is one of extraordinary violence, extraordinary fragility, and extraordinary complexity. The asteroid belt is not a junkyard, it is a laboratory where collisions happen at unimaginable speeds, where bodies are shattered and reassembled over timescales of hours, where the line between destruction and creation is not just thin, it is non-existent. The same impact that destroys a world can, in the right circumstances, create a new one. Hygeia, quiet, dark, round, and patient, is the proof. But there is a deeper truth lurking beneath all of this. A truth that goes beyond the specific science of asteroid impacts and rubble pile reassembly. A truth that connects Hygeia to the largest and most unsettling questions in planetary science. Questions about what counts as a world, about whether our definitions serve us or limit us, and about what it means to exist on the boundary between something and nothing. That deeper truth is where we go next. But before we reach that deeper truth, there are threads in the story of exploration that deserve fuller attention, because the attempts to understand Hygeia and objects like it are not a sequence of clean successes. They are a messy human process, full of wrong turns, bitter disagreements, lucky breaks, and agonizing near misses. The science is done by people, and the people bring their passions, their biases, and their stubbornness to the table. Consider, for example, the long and contentious history of asteroid family identification, the process by which scientists determine which asteroids belong to the same family, and, by extension, which ones were produced by the same catastrophic collision. The concept of asteroid families was first proposed in 1918 by the Japanese astronomer Kiyotsugu Hirayama, working at the Tokyo Astronomical Observatory. Hirayama analyzed the orbital elements of the known asteroids and noticed that some of them clustered together, not in physical space, but in orbital parameter space. Groups of asteroids shared similar semi-major axes, similar eccentricities, and similar inclinations, as though they had been launched from a common origin point and had drifted apart over time. Hirayama identified 3 major families in his initial analysis: the Coronis family, the Eos family, and the Themis family. His work was groundbreaking, but it was also limited by the small number of known asteroids at the time. In 1918, only a few hundred asteroids had been catalogued. Today, the count exceeds 1.2 million, and with each new asteroid added to the catalogue, the family picture has become more complex, more detailed, and more difficult to interpret. The Hygeia family was identified relatively late in the history of family studies. Its existence was proposed in the 1970s and refined in the 1980s and 90s as the number of known outer belt asteroids grew large enough to reveal the clustering in orbital element space. The identification was confirmed through spectroscopic surveys, measurements of the surface compositions of the family members, which showed that they shared IgGA's dark, carbonaceous spectral signature. The family was real, and its size, more than 6,800 members, placed it among the most populous families in the belt. But identifying the family was only the first step. The harder question was, what did the family tell us about the impact that created it? This is where the computational modeling became essential, and where the disagreements began. Early models of the Hygeia family formation assumed a relatively straightforward cratering event. A large impactor struck Hygeia's surface, excavated a massive crater, and launched the family members into nearby orbits. Under this scenario, Hygeia itself would have survived largely intact, with a huge crater as the only visible consequence. This model was simple, elegant, and widely accepted for decades. But it had a problem. The predicted crater was never found, and as observational techniques improved throughout the 2000s and 2010s, as larger telescopes with better adaptive optics systems were brought to bear on the problem, the non-detection of the crater became increasingly difficult to explain. If the crater existed, someone should have seen it by now. Its absence required either extraordinarily bad luck, every observation happening to catch Hygeia at an angle where the crater was hidden, or a fundamental error in the model. Some scientists proposed alternative explanations. Perhaps the crater had been erased by subsequent impacts, smaller collisions that had gradually filled in the basin and smoothed the surface over billions of years. This idea was plausible in principle, but difficult to support quantitatively. The crater was predicted to be so large, 200 kilometers or more, that filling it in would require an implausible number of subsequent impacts, each delivering enormous volumes of material to exactly the right location. The gardening hypothesis, as it was sometimes called, could not account for the complete absence of any trace of the original basin. Others suggested that the crater might be there but difficult to detect because of Hygeia's extremely low albedo. A crater on a surface that reflects only 5% of incident light might not show up in brightness-based observations because the contrast between the crater walls, the crater floor, and the surrounding terrain would be minimal. This explanation was more compelling, but it only pushed the problem to higher resolution observations. Eventually, someone would have an instrument sharp enough to see shape rather than brightness, and that instrument turned out to be SPARE. When SPARE revealed that the crater was genuinely absent, that the surface of Hygeia was smooth and featureless at the 25-kilometer resolution scale, the cratering model collapsed. The crater was not hidden, it was not filled in, it was not there, and the only model that could explain both the absence of the crater and the existence of the family was catastrophic disruption and reassembly. This model, first proposed in detail by Vanadza and colleagues in 2019, was not entirely new. The concept of catastrophic disruption had been discussed in the theoretical literature for decades, but it had never been applied to such a large body, and it had never been supported by such dramatic observational evidence. The combination of sphere shape data and the SPH simulations created a compelling, coherent picture. Total disruption, debris cloud formation, gravitational reaccumulation, spherical reassembly. But not everyone was convinced, and the disagreements that followed reveal a great deal about how science actually works when the stakes are high and the data is limited. One line of criticism focused on the simulations themselves. SPH simulations, while powerful, are computationally expensive and subject to significant uncertainties. The outcome of a simulated impact depends on the assumed properties of the target material, its density, its porosity, its fracture strength, its thermal state, and many of these properties are poorly constrained for C-type asteroids. Different assumptions about material strength can produce dramatically different results. A simulation that produces total disruption with one set of parameters might produce only a large crater with slightly different parameters. Critics argued that the simulations were not definitive. They showed that total disruption was possible, not that it was inevitable. A second line of criticism targeted the roundness measurement itself. While the SPEAR images clearly showed a roughly spherical body, the resolution was limited. The measured dimensions, 450 by 430 by 424 kilometers, are averages derived from a small number of images taken at different rotational phases. The uncertainties on these measurements are significant, roughly 10 to 20 kilometers on each axis. Within those uncertainties, Hygeia could be slightly more oblate or slightly more prolate than the best fit values suggest. Some critics argued that the body might be only approximately spherical, within the range of shapes that could be produced by a rotating rubble pile, without requiring hydrostatic equilibrium. A third criticism was more philosophical. Even if Hygeia is perfectly spherical, and even if its sphericity was produced by catastrophic disruption and reassembly, does that mean it is in hydrostatic equilibrium? The IAU's definition uses the phrase sufficient mass for its self-gravity to overcome rigid body forces. In a reassembled rubble pile, the rigid body forces are minimal. The body is not a rigid body at all, but a loose aggregate. Gravity does not need to overcome rigid body forces because there are no rigid body forces to overcome. The material is already in its lowest energy configuration. Is that equilibrium? Or is that simply the absence of resistance? The debate, as of today, remains unresolved. The IAU has not formally reclassified Hygeia. No vote has been called. No resolution has been proposed. Hygeia remains, officially, an asteroid, designated as minor planet number 10, the 10th asteroid to be numbered in the sequential catalogue of minor planets. Its designation belies its significance. It is one of the most scientifically important and poorly understood objects in the inner solar system, and yet it carries a number that suggests it is just another rock in a long list. There is a parallel in the history of science that is worth noting here. When Ceres was discovered in 1801, it was called a planet. Then, as more objects were found in the same region, it was demoted to an asteroid. For over a century and a half, Ceres was classified as a minor body, the largest asteroid, but still just an asteroid. It was only in 2006, when the IAU created the dwarf planet category, that Ceres was reclassified again. This time as a dwarf planet, the same category that Pluto had just been assigned to. Ceres's classification journey, planet to asteroid to dwarf planet, took 205 years. Hygeia's may be faster, or it may take just as long. The wheels of astronomical classification grind slowly, and the outcome depends not just on the science, but on the politics, the personalities, and the willingness of a community of scientists to confront the uncomfortable ambiguity that Hygeia represents. In the meantime, the data continues to accumulate. New observations of Hygeia are made periodically, refining its shape, its rotation, its thermal properties. New simulations are run, testing different impact scenarios, different material models, different initial conditions, and new discoveries in the broader asteroid belt, each one adding a data point to the evolving picture of small body dynamics, continue to refine our understanding of the processes that shaped Hygeia. The numbers from all of these investigations are striking. The asteroid belt contains roughly 1.2 million known objects and an estimated total population of several million. Of these, fewer than 30 are larger than 200 kilometers in diameter. Only 4 are larger than 400 kilometers. And of those 4, one, Hygeia, is round in a way that it should not be, smooth in a way that defies explanation, and silent in a way that challenges everything we thought we understood about the small bodies of the solar system. 5 missions, 5 windows into the physics of asteroids, and all of them, in different ways, point toward the same unsettling conclusion. The asteroid belt is not a collection of simple, inert rocks. It is a dynamic, violent, constantly evolving system, where bodies are built and destroyed and rebuilt in an endless cycle of creation and annihilation. And somewhere in that cycle, at a specific moment in the deep past, under conditions that we can model but never directly observe, the original Hygeia was annihilated, and the Hygeia we know today was born. The question that remains is not scientific, it is philosophical, and it is, in its own quiet way, the most profound question that Hygeia asks. Does the manner of a world's creation determine whether it deserves to be called a world at all? There is another thread in the tapestry of exploration that deserves attention here, one that does not involve a specific mission or spacecraft, but rather a revolution in how we observe the asteroid belt from the ground. And this revolution, which began in the early 2000s and continues to accelerate today, is changing the Hygeia debate in ways that the earlier generation of observers could never have imagined. The revolution is called large-scale sky surveys. Projects like the Sloan Digital Sky Survey, the Catalina Sky Survey, and the Pan-STARRS survey on Haleakala in Hawaii have systematically scanned the sky over the past 2 decades, cataloguing millions of objects, stars, galaxies, quasars, and asteroids. These surveys do not target individual objects. They sweep the entire visible sky, night after night, recording the positions and brightnesses of everything they detect. And in the process, they have discovered hundreds of thousands of new asteroids, including many new members of the Hygeia family. Before these surveys, the Hygeia family was thought to contain perhaps 1,000 known members. Today, The count exceeds 6,800, and it continues to grow. Each new member adds a data point to the family's total mass estimate, which in turn refines the models of the original impact. The more family members we find, the better we can constrain the energy of the collision, the size of the impactor, and the dynamics of the debris cloud. And every refinement has pushed the models further in the direction of total disruption. But the surveys have also revealed something unexpected. The Hygeia family is not distributed uniformly across its orbital neighborhood. It has structure. The family members cluster in certain regions of orbital element space and avoid others. There are gaps, regions where family members are conspicuously absent, that correspond to gravitational resonances with Jupiter. And the distribution of family members as a function of size follows a specific pattern, a power law, that carries information about the fragmentation physics of the original impact. Analyzing these patterns requires sophisticated statistical techniques and massive computational resources. Teams of researchers have spent years modeling the family's orbital evolution, accounting for the effects of gravitational perturbations from Jupiter and Saturn, the slow orbital drift caused by the Yarkovsky effect, a subtle force produced by the asymmetric re-emission of absorbed sunlight, and the chaotic interactions between family members themselves. The goal is to reconstruct the family's original configuration at the time of the impact, and to determine, as precisely as possible, when the impact occurred. The best current estimates place the age of the Hygeia family at roughly 2 billion years, give or take several hundred million years. That means the impact that created the family and that shattered and reassembled Hygeia occurred roughly 2 billion years ago. At that time, Earth was a very different place. The continents were gathered into a supercontinent called Columbia or Nuna. The atmosphere contained almost no free oxygen. Life consisted entirely of single-celled microorganisms, bacteria and archaea, with no complex multicellular organisms anywhere on the planet. The dinosaurs would not appear for another 1.7 billion years, 2 billion years. That is how long ago Hygeia died and was reborn. And in those 2 billion years, its reassembled surface has been slowly modified by the steady rain of micrometeorites, tiny particles of dust and rock that impact its surface at speeds of several kilometers per second, each one too small to leave a visible crater, but collectively powerful enough, over billions of years, to grind the surface into a fine-grained regolith, a blanket of dust and tiny fragments that covers the underlying rubble like a layer of dark flour. This regolith, this thin, powdery coating, is what we see when we observe Hygeia from Earth. We are not looking at the reassembled rubble directly. We are looking at a skin of dust draped over the rubble, smoothed and homogenized by 2 billion years of micrometeorite bombardment. The featurelessness of the surface is not just a consequence of the reassembly. It is a consequence of time, of the patient, relentless grinding that has erased whatever subtle textures the reassembly process might have left behind. This adds yet another layer of complexity to the Hygeia mystery. We are trying to determine the nature of a body whose surface has been processed and modified for 2 billion years, whose interior structure is unknown, whose composition is only broadly constrained, and whose formation history is reconstructed entirely from computer simulations and indirect evidence. We are, in a very real sense, trying to read a book whose pages have been bleached by the sun and whose cover has been worn smooth by time. The words are there somewhere, but reading them requires instruments and techniques that we have not yet built. And that is perhaps the most frustrating aspect of the Hygeia story, the gap between the questions we can ask and the questions we can answer. We know enough to see the puzzle. We know enough to understand why it matters, but we do not know enough to solve it. Not yet. Not without a mission. Not without a spacecraft in orbit, taking measurements that only proximity can provide. Gravity field data, seismic recordings, high-resolution surface images, compositional maps, density profiles. The instruments exist. The technology is mature. What is lacking is the will, the funding, the political support, the institutional enthusiasm to send a mission to a dark, obscure asteroid that most people have never heard of. In the global hierarchy of space exploration priorities, Hygeia ranks low. It is not as photogenic as Mars. It is not as dramatic as a comet. It does not have the cultural cachet of Pluto or the astrobiological appeal of Europa. It is small, dark, far away, and difficult to see. And yet it holds a key to one of the most fundamental questions in planetary science. What is a world? Where do we draw the line? And who gets to decide? These are not questions that a telescope can answer. They are questions that require a combination of data and philosophy, of measurement and judgment. They are questions that live at the intersection of science and human values. The intersection where we decide not what the universe is, but what we choose to call it. And that intersection, for now, remains unresolved. Hygeia orbits, the sun shines, the rubble holds its shape, and the question, world or rock, planet or debris, something or nothing, hangs in the cold, dark silence of the outer belt, waiting for an answer that may not come in our lifetime. There is one more attempt worth documenting, one that is less a mission and more a mindset shift, and it has shaped the Hygeia debate in ways that are easy to overlook. In 2018, a year before the sphere observations, a group of planetary scientists led by Philip Metzger published a paper that argued, on historical and scientific grounds, that the IAU's 2006 definition of a planet was fundamentally flawed. Metzger and his colleagues reviewed over 200 years of scientific literature, going back to Galileo, and found that the concept of clearing the orbit had never been used as a criterion planehood before the 2006 vote. The historical practice, they showed, was consistently geophysical. A planet was defined by what it was, not by where it orbited. A body large enough for its gravity to make it round was, by long-standing scientific tradition, a planet, period. This paper did not mention Hygeia. It was published before the spare results. But its arguments anticipated the Hygeia debate with uncanny precision, because if the geophysical definition is correct, if roundness is sufficient for planehood, then Hygeia is a world, regardless of its orbital neighborhood, regardless of how it achieved its roundness, and regardless of whether the IAU ever votes to reclassify it. Metzger's paper was widely read, widely cited, and widely debated. It gave scientific legitimacy to a position that many planetary scientists had held privately for years. The IAU definition was bad science, driven by political compromise rather than physical insight, and it provided a framework, a vocabulary, a set of arguments, a historical grounding for the debate that Hygeia would soon ignite. The confluence of these efforts, the missions, the surveys, the theoretical work, the definitional debates, has created a scientific moment, a moment when our understanding of small bodies is expanding faster than our categories can accommodate, a moment when the data is outpacing the definitions, a moment when a dark, round, silent body in the outer asteroid belt is forcing the entire field of planetary science to ask itself, what are we really studying? What are the things that orbit our star? And what do we owe them, in terms of attention, in terms of naming, in terms of respect? These are the questions that the deeper truth of Hygeia will ultimately force us to confront, and it is to that deeper truth that we now turn, because what Hygeia reveals, when you step back from the technical details and the classification debates and the orbital mechanics, is something simple and unsettling about the nature of knowledge itself. Every mission in this chapter, Dawn, Hayabusa 2, Lucy, Psyche, Dart, was designed to answer specific questions, and every one of them, without exception, raised more questions than it answered. That is not a failure of the missions. That is the nature of exploration. The more we learn about the asteroid belt, the less certain we become about what it contains. And Hygeia, dark and patient and round, is the embodiment of that uncertainty, a world-shaped question, orbiting the sun in silence, waiting for us to build the instrument that can finally provide an answer. Begin with a thought experiment. Imagine you are standing on the surface of Hygeia. It is, first of all, dark. Not dark the way a moonless night on Earth is dark, where the sky still glows faintly with scattered starlight and the distant haze of human civilization. Dark the way a cave is dark. A blackness so complete that your sense of spatial orientation begins to dissolve. The surface beneath your feet is blacker than charcoal, blacker than wet basalt, blacker than anything you have ever seen in nature. It absorbs more than 94% of the sunlight that touches it. At 3 times the Earth's distance from the sun, that sunlight is already thin, reduced to about 1/9 of its intensity at the orbit of our home planet. What little light arrives is swallowed almost entirely by the ground. You stand on a world that eats its own illumination. Look up. The sun is there, but it is small, a brilliant point of light, unmistakably brighter than any star, but no longer the warm, swollen disk that dominates Earth's daytime sky. It has been reduced to a fierce jewel, a glowing needle that casts sharp, thin shadows across the terrain, but provides no warmth you can feel through your suit. The surface temperature around you hovers near 160 Kelvin, roughly 113 degrees below 0 Celsius. Cold enough to make carbon dioxide freeze into dry ice, cold enough that most organic chemistry simply stops. This is not a place that invites biological speculation. This is a place where chemistry itself retreats into stillness. But look down, look at the horizon, and here is where the strangeness begins to register, not as data, not as a measurement, but as a feeling, a disorientation that settles into your chest before your brain can articulate why. The horizon is close. Hygeia's diameter of roughly 430 kilometers gives it a circumference of about 1,350 kilometers, which means that if you are standing upright on its surface, the horizon is only about 2 kilometers away. On Earth, the horizon sits roughly 5 kilometers distant. On the Moon, roughly 2.4 kilometers. On Hygeia, the curve of the ground drops away so rapidly that you can almost see it turning, a visible, palpable rounding of the world beneath your feet. You are standing on a sphere, and you can feel it, not through your instruments, not through your telemetry, but through the simple act of looking out at the edge of the ground and watching it fall away faster than your instincts expect. And that sphere, that visible, tangible, undeniable roundness, is the heart of the mystery, because Hygeia has no business being round. Everything we know about physics, about gravitational self-organization, about the mechanical properties of silicate rock and carbonaceous rubite, says that a body this small should be a lumpy, irregular mass. It should look like Vesta or Pallas or any of the thousands of other mid-sized asteroids that populate the belt in all their misshapen glory. Hygeia should be a potato. It is, instead, a pearl. And the story of how it came to be a pearl, the catastrophic destruction, the cloud of debris, the slow gravitational reaccumulation in the silence of deep space, is one of the most extraordinary tales of transformation in the entire solar system. But here is the thing that has been nagging at the edges of this narrative from the very beginning, the thing that the classification debate circles around without ever quite grasping directly. The question of whether Hygeia is a dwarf planet or an asteroid is not really a question about Hygeia. It is a question about us. It is a question about the categories we build to organize the universe, and what those categories reveal, not about the objects they contain, but about the minds that created them. Consider for a moment how strange the entire enterprise of classification really is. The universe does not arrive pre-sorted. Stars do not wear labels. Planets do not carry birth certificates. The vast, silent machinery of physics produces an unbroken continuum of objects, from particles of interstellar dust weighing less than a microgram to supermassive black holes containing the mass of 10 billion suns, and at no point in that continuum does nature insert a dividing line and declare, here. This is where one category ends and another begins. All such lines are drawn by human beings, for human reasons, to satisfy human needs. They are useful, they are sometimes necessary, but they are never natural. They are always, at bottom, a confession of our own cognitive architecture. The architecture of a brain that evolved to sort berries and predators and members of rival tribes into categories that served survival, now turned loose on a cosmos that does not sort itself. This is not a criticism of taxonomy. Classification is one of the most powerful intellectual tools our species has ever developed. Without it, science itself would be impossible. You cannot study what you cannot name. You cannot compare what you cannot categorize. The entire history of biology, from Linnaeus to modern genomics, is a history of classification, of looking at the overwhelming diversity of living things and finding patterns, groupings, hierarchies that make the complexity manageable, that transform a bewildering swarm of organisms into a structured narrative of evolution. The periodic table is a classification. The standard model of particle physics is a classification. Every map, every catalogue, every database is an act of classification. The human mind is, at its most fundamental level, a classification engine. But the power of classification comes with a cost. When you draw a line, you create two sides. And the moment those two sides exist, they begin to accumulate cultural weight, institutional inertia, and emotional significance that far exceeds the original act of drawing. Think about the word planet. Before 2006, it was a word that most people used without thinking, a category so familiar, so obviously natural, that questioning it felt absurd. There were 9 planets. Everyone knew that. Children memorized them. Teachers taught them. Textbooks listed them. The number 9 had become, through decades of repetition and cultural embedding, not just a fact but an identity. To be a planet was to matter. To be something else, an asteroid, a comet, a Kuiper belt object, was to be lesser. And then the IAU voted, and Pluto was reclassified, and the response was immediate, visceral, and disproportionate. People were angry, not mildly annoyed, not academically concerned, genuinely angry, in a way that surprised even the astronomers who had advocated for the change. The state legislature of New Mexico passed a resolution declaring that Pluto would always be considered a planet within the state's borders. The Illinois State Senate did the same. Children wrote letters of protest to NASA. A verb was briefly popularized, to Pluto someone, meaning to demote or devalue them. The emotional response to Pluto's reclassification was, by any reasonable measure, wildly out of proportion to the scientific significance of the change. Pluto itself was not affected. Its orbit did not change. Its composition did not change. Its moons did not disappear. The only thing that changed was a word, a label, a line on a chart that existed only in human minds and human documents. And yet the grief was real. The anger was real. The sense of loss was real. Because classification is never just classification. It is always, simultaneously, an act of valuing. When we place something in a category, we are not merely describing it. We are assigning it a rank, a significance, a degree of worthiness in the hierarchy of things we care about. Planets matter. Asteroids do not. Dwarf planets matter a little. They get the word planet in their name, at least, but not as much as the real ones, the official ones, the 8 that made the cut. This hierarchy is never stated explicitly, because stating it would reveal how absurd it is. Does Neptune really matter more than Pluto? Does Jupiter deserve more attention than Ceres? Of course not. But the categories imply it, and the implications become, over time, self-fulfilling. We send missions to planets. We build telescopes to study planets. We write books about planets. The things we do not call planets receive less funding, less attention, less love. The line creates the hierarchy, and the hierarchy creates the reality. Hygeia exposes this machinery with particular clarity, because it is such an unlikely candidate for the debate. If you were designing a test case for the dwarf planet classification, a body specifically engineered to probe every weakness and ambiguity in the IAU definition, you could hardly do better than Hygeia. It is round, but only because it was destroyed and reassembled. It is in hydrostatic equilibrium, but only if you accept that rubble piles can achieve equilibrium through a mechanism different from the one the original definition imagined. It has not cleared its orbit, but neither has any other asteroid, so that criterion provides no useful discrimination within the belt. It orbits the Sun. It is not a moon. It meets some criteria and fails others and problematizes the rest. It is, in the language of philosophy, a hard case, the kind of case that forces a rule to reveal its assumptions. And the assumption that Hygeia reveals is this. The IAU definition of 2006 was not designed to accommodate objects like Hygeia. It was designed to solve the Pluto problem, to create a category that included the 8 classical planets and excluded Pluto, Eris, and the growing swarm of Kuiper belt objects that threatened to inflate the planet count to absurd numbers. The definition was, from the start, a political compromise masquerading as a scientific criterion. It was built to produce a specific result, and it succeeded. But the universe, indifferent to human politics, continued producing objects that the definition could not handle. Hygeia is one of those objects. Sedna is another. Quaoar, Orcus, Cilicia, Gongong. The outer solar system is populated with bodies that exist in the gaps between the categories, bodies that are too large to ignore and too ambiguous to classify, bodies that sit on the wrong side of every line we try to draw. This proliferation of ambiguous objects is not a problem to be solved. It is a feature of reality to be acknowledged. The universe does not produce objects in neat categories. It produces a continuum, an unbroken spectrum of sizes, compositions, orbital configurations, and formation histories that resist every attempt at clean division. When we draw a line and say, everything above this line is a planet, and everything below it is not, we are imposing a discrete boundary on a continuous distribution, and the result is always the same. Objects cluster near the boundary, and the boundary itself becomes the site of an irresolvable argument. This is not unique to astronomy. It happens in every field that attempts to classify a natural continuum. What is the difference between a hill and a mountain, between a stream and a river, between a pond and a lake, between a species and a subspecies? These boundaries are all, without exception, drawn by human agreement rather than discovered in nature. They are useful. A geographer needs to distinguish mountains from hills. A biologist needs to distinguish species from subspecies. But they are never clean. There are always borderline cases. There are always objects that sit on the line and refuse to move to one side or the other. And the debates about those objects are never really about the objects themselves. They are about the categories, about whether our intellectual infrastructure is adequate to the reality it is trying to describe. Hygeia is a mountain that might be a hill, and the argument about which one it is reveals, with uncomfortable clarity, that we never had a good definition of either. But there is a second layer to the Hygeia story that goes beyond classification and into something more fundamental, something about the nature of destruction and creation, about the relationship between chaos and order, about the way the universe builds complex structures from simple ingredients through processes that we are only beginning to understand. Consider, once more, what happened to Hygeia roughly 2 billion years ago. A body approximately 100 kilometers across, a small world in its own right, a mass of rock and ice and carbon compounds that had been orbiting the Sun since the formation of the solar system, struck the original Hygeia at a speed of approximately 7 kilometers per second. The energy released was almost beyond human comprehension. The impact did not merely create a crater. It did not merely gouge out a chunk of the surface. It shattered the entire body. Every cubic kilometer of rock was broken, fragmented, pulverized into a cloud of debris that expanded outward from the collision point, like a slow-motion explosion. For a brief window of time, hours, perhaps days, the object that had been Hygeia ceased to exist. There was no Hygeia, there was only a cloud, and then gravity did something remarkable. Slowly, patiently, with no blueprint and no guidance and no intention, the fragments began to fall back together. The largest pieces attracted the smallest. Clumps formed, merged, grew. The rubble sorted itself, not perfectly, not efficiently, but relentlessly, into a new configuration. And when the process was complete, when the last fragments had settled and the last tremors had faded, and the cloud had collapsed back into a single coherent body, what remained was a sphere. Not the original Hygeia, which had been a differentiated protoplanet with a distinct iron core and rocky mantle. A body with structure, with layers, with a geological history written into its internal architecture. That Hygeia was gone forever. What replaced it was something fundamentally different. A rubble pile, a gravitational aggregate, a ball of shattered fragments held together by nothing more than their own mutual attraction. And it was round. This is the fact that stops you if you sit with it long enough. The catastrophe did not produce chaos, it produced order, the most violent event in Hygeia's history. An event that literally unmade the world, resulted not in a jagged, scarred, misshapen ruin, but in a shape so symmetrical, so geometrically perfect, that it satisfies the strictest mathematical definition of an oblate spheroid. Destruction gave rise to creation. The end of one world was the beginning of another, and the new world, born from violence, was more beautiful, more regular, more balanced, more aesthetically pleasing to the human eye than the old one had been. There is something almost mythological about this transformation. Cultures across the world have stories of destruction and rebirth, of floods that wipe clean the corruption of an old world and allow a new one to emerge, of fires that consume the forest and leave behind soil, enriched for new growth, of gods who are torn apart and whose scattered pieces become the foundations of a new creation. The Norse had Ragnarök, the apocalyptic battle that destroys the old gods and gives rise to a green, renewed earth. The Hindu tradition has the cycle of creation and dissolution, Brahma's day and Brahma's night, in which the universe is born, lives, dies, and is born again in an endless rhythm. These are not scientific narratives, but they capture something that the Hygeia story also captures: the deep counterintuitive truth that destruction and creation are not opposites. They are partners. They are phases of the same process. The universe does not build things and then break them. It builds things by breaking them. This is visible at every scale. Stars are born from the gravitational collapse of gas clouds, clouds that were themselves produced by the explosive deaths of earlier stars. The heavy elements that make up your body, the calcium in your bones, the iron in your blood, the carbon in every molecule of your DNA, were forged in the interiors of stars that no longer exist, scattered into space by supernova explosions, and swept up billions of years later by the gravitational pull of a forming solar system. You are, in a very literal sense, made of debris. You are a rubble pile. You are the reassembled fragments of catastrophes that occurred before the sun was born. And Hygeia, in its own quiet way, is a mirror of that process. It is a body that was destroyed and remade, that emerged from its own annihilation as something new, something different, something that, depending on which definition you choose, might qualify as a world. The rubble pile found its shape. The debris settled into equilibrium. The chaos became order. And now it orbits, silent and dark and round, carrying in its interior the memory of a violence so total that nothing survived it except the matter itself, the atoms, the molecules, the raw material of a world, reassembled by gravity into a form that gravity itself seems to prefer. This preference, gravity's tendency to pull matter into spheres, is one of the deepest facts about the geometry of the universe. A sphere is the shape that minimizes surface area for a given volume. It is the shape that distributes internal stress most evenly. It is the shape that a self-gravitating body will adopt when its own gravitational energy exceeds the structural strength of its material. Gravity does not know any of this, of course. Gravity has no knowledge, no intention, no aesthetic preferences. It is simply a consequence of the curvature of space-time in the presence of mass, a geometrical property of the universe that Einstein described in 1915 and that operates with serene indifference across every scale, from subatomic particles to galaxy clusters. But the result of this blind, mindless mathematical process is beauty. Spheres, circles, the round faces of planets, the round disks of galaxies, the round shells of expanding supernovae. The universe is drenched in roundness, saturated with it, and Hygeia's unexpected sphericity is just one more expression of a pattern that extends from the smallest soap bubble to the largest observable structure in the cosmos. There is a temptation, when confronting this kind of beauty, to see purpose in it, to interpret the mathematical elegance of physical law as evidence of design, of intention, of a universe that is trying to produce something. That temptation is understandable. It is also, as far as science can determine, unfounded. The beauty of physics is real, but it does not require an author. A sphere is beautiful because our brains evolved to find symmetry pleasing, and our brains evolved in a universe where symmetry correlates with structural integrity, with health, with fitness. We find spheres beautiful because we are products of the same gravitational processes that produce spheres. The beauty is not in the object. It is in the resonance between the object and the observer, a resonance that exists because both the object and the observer were shaped by the same underlying physics. Hygeia does not know it is beautiful. It does not know it is round. It does not know that a team of scientists in Marseille spent months analyzing its shape and published a paper that generated headlines around the world. It does not know that its existence has fueled a debate about the definition of a planet that has engaged hundreds of researchers across dozens of institutions on 6 continents. It orbits in silence. It rotates in darkness. It is by any human standard spectacularly indifferent to the attention it has received. And yet we attend to it, we care, we argue. We build telescopes and design instruments and write proposals and compete for observation time and process data and publish papers and hold conferences and revise definitions, all because of a dark, cold, silent body orbiting the Sun at a distance of roughly 470 million kilometers. A body that reflects less light than a charcoal briquette, and that has never, in the entire history of human civilization, been visible to the unaided eye. Why? Why does it matter? Why should anyone care whether Hygeia is classified as an asteroid or a dwarf planet? The honest answer is that it should not matter, and it matters enormously. It should not matter because classification is a human convenience, and Hygeia's physical properties are unchanged regardless of what label we attach to it. Its mass does not increase when we call it a dwarf planet. Its surface does not brighten. Its orbit does not shift. The label is about us, not about Hygeia. In the grand scheme of the cosmos, the question of whether a 430-kilometer rubble pile in the asteroid belt deserves to be called a planet of any kind is so trivially unimportant that it barely registers against the background noise of reality. But it matters enormously because the act of classification is the act of paying attention. When we argue about whether Hygeia is a world, we are forcing ourselves to look at it, to study it, to think about it, to take it seriously as an object worthy of investigation. The debate itself is a form of attention, and attention is the scarcest resource in science. There are more objects in the solar system than there are scientists to study them, more questions than there are grants to fund answers, more data than there are hours in a lifetime to analyze. The things we choose to classify are the things we choose to study, and the things we choose to study are the things we come to understand. Classification is not just labeling, it is prioritization. It is the mechanism by which science decides what deserves its limited time and resources and passion. If Hygeia is reclassified as a dwarf planet, it will matter, not because the reclassification changes Hygeia, but because it will change us. It will change the conversations we have about the asteroid belt. It will change the proposals that get written, the missions that get funded, the textbooks that get published, the curricula that get taught. It will move Hygeia from the margins of planetary science to something closer to the center. It will make it visible in a way that it has never been visible before. And visibility, in science, is the beginning of understanding. This is why the classification debate, for all its apparent triviality, is not trivial at all. It is a debate about attention. It is a debate about what we consider worthy of our time, our money, our curiosity, our care. And it is a debate that Hygeia, in its dark and silent way, is winning, because every paper published, every conference talk delivered, every headline written about the possible dwarf planet in the asteroid belt is a small act of attention, a small investment of human consciousness in an object that, 20 years ago, almost no one thought about at all. There is a final thought worth lingering on, and it has to do with time. Hygeia has been orbiting the Sun for approximately 4.5 billion years. For the first 2.5 billion of those years, it was a different body, a primordial object, perhaps partially differentiated, with a structure and a surface and a geological identity that we will never know in detail because that body no longer exists. Then came the impact. Then came the destruction, the cloud of debris, the slow reassembly, and for the last 2 billion years, the current Hygeia, the rubble pile, the gravitational aggregate, the dark and spherical enigma, has been orbiting in the same region of space, slowly processing its surface through the patient, ceaseless weathering of the space environment. 2 billion years. That number, spelled out, is so large that it resists comprehension. But consider some comparisons. 2 billion years ago, the most complex life on Earth was single-celled. Multicellular organisms did not yet exist. The atmosphere contained almost no free oxygen. The continents were arranged in a configuration that would be unrecognizable to a modern geographer. A world of barren rock and shallow, iron-rich seas, with no forests, no grasslands, no animals, no soil. Everything that we think of as the history of life, the Cambrian explosion, the age of dinosaurs, the rise of mammals, the evolution of primates, the emergence of human beings, the invention of language, the development of agriculture, the construction of cities, the creation of science. All of that has occurred since Hygeia was destroyed and reborn. The current Hygeia is older than complex life on Earth. It achieved its present form before the first multicellular organism assembled itself from cooperating cells in a warm Proterozoic ocean, and it will outlast us. Barring an improbable collision with another large body, Hygeia will continue to orbit the Sun long after human civilization has ended, long after our species has evolved into something unrecognizable or gone extinct, long after the texts of our debates and the data from our telescopes have been lost to entropy and time. The classification question that consumes us now, world or rock, planet or debris, will be forgotten. The IAU will dissolve. The journals will decay. The servers that store our data will fail and fall silent. But Hygeia will still be there, dark and round and cold, orbiting with the same patient indifference that has characterized its existence since the day it reassembled itself from its own wreckage. There is something humbling about this perspective. Not humbling in the way that the word is usually used. Not a gentle, warm humility that makes you feel connected to something larger. Humbling in a sharper, more unsettling way. The realization that the questions we spend our careers arguing about are, from the perspective of the objects themselves, utterly meaningless. Hygeia does not care if it is a dwarf planet. The Sun does not care if we have a consistent taxonomy of the objects that orbit it. The universe does not care if our categories are logically coherent. These are human concerns, born of human brains, serving human purposes. They matter to us because we are the kind of creatures who need to sort the world into categories in order to understand it. But the world itself, the real physical, gravitational, thermodynamic world of matter and energy and space-time, has no need for our categories. It simply is. And Hygeia simply is. It is round. It is dark, it is cold, it is old, it is made of rubble, it was destroyed and reborn. It orbits the Sun at a mean distance of roughly 3.14 astronomical units, completing one orbit every 5.5 years. It rotates once every 27.6 hours. It has a density of approximately 2.06 grams per cubic centimeter. It reflects about 5.4% of the sunlight that reaches it. These are facts. They are not affected by our definitions. They will remain true regardless of what we call the object that possesses them. But we are creatures who name things. We are creatures who classify, who categorize, who sort and label and organize and debate. It is one of our deepest impulses, perhaps the deepest, more fundamental even than language itself, since you must categorize the world before you can describe it. And so we will continue to argue about Hygeia. We will continue to refine our definitions, propose new criteria, analyze new data, publish new papers. We will send missions, eventually, inevitably, to visit it, to orbit it, to map its surface and probe its interior, and measure its gravity, and determine once and for all whether its roundness is the roundness of a world in hydrostatic equilibrium, or the roundness of an accident, a statistical fluke, a gravitational coincidence. And when those measurements are made, when a spacecraft finally arrives at Hygeia and begins transmitting data back to Earth across 400 million kilometers of empty space, the answer will not settle the debate. It will deepen it. It will reveal new complexities, new ambiguities, new reasons to argue. Because that is what exploration does. It does not provide closure. It provides depth. It does not answer questions. It reveals how much more complicated the questions were than we ever imagined. The Dawn mission went to Ceres expecting to find a dead, frozen asteroid. It found a geologically active body with a subsurface ocean and organic chemistry. Hayabusa 2 went to Ryugu expecting to collect samples from a solid body. It found a rubble pile so porous that its density was barely higher than water. DART struck Dimorphos expecting a predictable response. The response was larger than any model had forecast. Every mission to a small body has overturned assumptions, and a mission to Hygeia would do the same. The universe is more complicated than our models. It is always more complicated than our models. And Hygeia, sitting at the intersection of so many unresolved questions about catastrophic disruption, about hydrostatic equilibrium, about rubble pile mechanics, about the definition of a world, is likely to be more complicated than all of them. This is not a reason for despair. It is a reason for wonder. The fact that the universe consistently exceeds our capacity to describe it is not a failure of science. It is the engine of science. If the universe were simple enough to fit neatly into our categories, there would be nothing left to discover. The borderline cases, the Hygeias, the Plutos, the objects that refuse to sit quietly on one side of our lines, are the most scientifically valuable objects of all, precisely because they expose the limitations of our thinking and force us to think again. So let us return, one last time, to the image that started this entire story. A team of astronomers in Marseille, processing data from a telescope in Chile, staring at a screen that shows something impossible. A sphere, a perfect, dark, featureless sphere, orbiting the Sun in the asteroid belt, where no sphere should be. The image is small, a handful of pixels, a smudge of light resolved into something with a shape. It is not dramatic. It is not beautiful in the way that a Hubble photograph of a nebula is beautiful, or a Cassini image of Saturn's rings is beautiful. It is a blob, a round blob, an impossibly, inexplicably, wonderfully round blob. But look at it closely, look at what it represents. That blob is the portrait of a world that was shattered and reassembled, a body that endured the most violent event imaginable and emerged from it in the most perfect shape in nature. That blob is a challenge to every definition we have ever written, every category we have ever constructed, every line we have ever drawn between world and not world. That blob is a 2 billion-year-old testament to the capacity of gravity to create order from chaos, beauty from destruction, spheres from rubble. That blob is, depending on your definition, either the smallest dwarf planet in the solar system or the largest asteroid, and the fact that we cannot decide which one it is tells us more about the nature of knowledge than either answer ever could. Hygeia orbits. The Sun shines upon it dimly from 470 million kilometers away. The surface, darker than midnight, absorbs the light and gives nothing back. The rubble, the billions of fragments of a world that died 2 billion years ago, holds its shape, bound by nothing more than gravity, organized by nothing more than physics, round for no reason other than the geometry of the universe. It does not know what it is. It does not need to know. That question is ours, and ours alone. And we are still, after all these years and all these arguments and all these telescopes and all these papers, trying to find an answer worthy of the object that inspired it. Some questions are not meant to be answered. They are meant to be lived with, carried forward, generation after generation, each new cohort of scientists adding a measurement, a model, a refinement, a new piece of data that makes the picture slightly clearer and the question slightly deeper. The question of what Hygeia is, world or rock, planet or debris, something or nothing, is one of those questions. It will not be resolved by a vote. It will not be settled by a definition. It will be carried, patiently and imperfectly, by every scientist who takes the time to point a telescope at a dark corner of the asteroid belt and wonder what is hiding there in the silence between Mars and Jupiter. That act of wondering, that impulse to look, to measure, to name, to argue, to care about a cold, dark body that will never be about us, is the most human thing we do. It is the thing that separates us from the rubble. We are matter that has learned to ask questions about itself. We are debris that has organized itself into consciousness. We are, in our own way, rubble piles, assembled from the fragments of dead stars, held together by forces we did not choose, shaped by processes we are only beginning to understand. And perhaps that is why Hygeia fascinates us. Not because it might be a dwarf planet, not because its roundness challenges a definition, not because its history rewrites the story of catastrophic disruption in the asteroid belt, but because, in its dark and silent way, it mirrors something true about our own condition. We too were assembled from debris. We too carry the memory of ancient catastrophes in our atoms. We too found our shape through processes that we did not control and do not fully understand. And we too are trying imperfectly, stubbornly, with all the tools and categories and definitions at our disposal, to make sense of a universe that is under no obligation to make sense to us. Hygeia does not answer that effort, but it honors it. By being what it is, complex, ambiguous, beautiful, strange, it gives us something to reach toward, a mystery to solve, a world to understand, a question to carry. And out there, in the cold, dark silence of the asteroid belt, 470 million kilometers from the nearest human thought, it orbits, patient, round, waiting.